seen before. I have to start out by acknowledging many people who have contributed bits of data and code and lattices that without which this workshop would absolutely not have been possible. Here's the one-slide summary of what we're doing. I'm going to give a 15-minute summary of what, or well, 15 to 30 minutes, depending on how many questions there are, summary of what we're doing, but here's the one-slide summary. Our project this summer has broadly a scientific objective and a technological objective. The scientific objective is to use some of the many things that we know about human speech psychology and about phonetics in order to design a new architecture for automatic speech recognition. The technological motivation for doing so is that speech is the dependencies in the speech signal and the linguistic dependencies and the acoustic dependencies span huge time scales. They span several levels of linguistic hierarchy. And we would like to be able to learn something about how speech is organized in this tremendously high-dimensional space. And in order to learn how speech is organized in this tremendously high-dimensional space, we're proposing to use structured machine learning methods and regularized machine learning methods, which are somewhat different from the usual approaches. And in order to design those structures, we have looked to the psychology literature and the linguistics literature. The systems that we've implemented and tested over the summer can be broadly grouped into four subsystems. First of all, several of us have spent quite a bit of effort on binary phonetic classifiers. When we started this summer, we had very high-quality manner classifiers already, and those have not really improved in the course of the summer, but our place of articulation classifiers have improved, in some cases dramatically, depending on how much attention any one of the researchers paid to the particular place classification problem. So in some case, the place of articulation of a stop release, for example, the error rate has dropped by as much as 50%. That's the classification error rate. Second and third, we have two different pronunciation models that can actually generate pronunciation scores or recognition scores that can be used to augment the information in a word lattice. And those two different pronunciation model scores are a generative model and a discriminative model. The generative model is a dynamic Bayesian network based broadly on articulatory phonology. The discriminative pronunciation model is a targeted classification algorithm designed essentially to take advantage of all of the information that we have available from the lattices that were produced by the first pass recognition system, and to do basically to do targeted phonetic classification only when it's necessary in order to correct errors in the lattice. And then finally, we've developed a new maximum entropy score combination technique, which is actually quite a bit can be applied to it seems to me can be applied to essentially any kind of word level side information that one might wish to incorporate into any type of current automatic speech recognizer. Our bottom line results are not significant yet. We have been trying our goal, stated numerical goal for this project was to reduce the word error rate on the rich text, on the DARPA-EARS rich text speech data. We have reduced the error rate of the development set, but not by a statistically significant amount. So the overall numerical bottom line is currently not publishable. Here's an outline of the things that we are covering in this talk. First of all, what is the motivation for doing this? Why should we believe that landmarks are going to make a difference? Why are we using a lattice rescoring paradigm to test the landmarks? Because that's not obvious, and there are some problems that I'll discuss. What are the systems that we've developed? These are in particular the two pronunciation models, and then I'll talk a little bit about what the future plans are, and I'll introduce the next speakers. The scientific motivation for this project is based on models of human speech perception and human speech production. The umbrella model of human speech perception is something called landmark-based speech perception, which proposes that most human speech recognition pays attention to peaks and dips in energy in the signal and to changes in the manner of articulation of the signal. The extra attention paid to sudden changes in the spectrum is well documented in neurophysiology. In psychology dealing with human beings, we have a couple of psychological results. One is that humans are able to recognize consonants basically at chance if you give them 10 or 20 milliseconds around the release, and if you extend that to some critical period of time of a window of 25 to 35 milliseconds following the release of the consonant, suddenly within a span, a change of 10 milliseconds or so, human performance goes up to rather close to perfect. Second, humans also, it turns out, recognize vowels better if they're given just the onset of the vowel and just the offset of the vowel than they are if they're given all of the other glottal pulses from the center of the vowel. Rather a counterintuitive result. Our results this summer support this for the case of classifying stops, nasals, and fricatives. If we tried to classify the place of articulation of one of those consonants using information that's centered at the release or the closure of the consonant, our classification error rates are a factor of 2 or more less than our classification error rates if we tried to classify a stop, nasal, or fricative using a frame taken from the center of the consonant. This rather goes without saying for stop consonants, but it's even true for fricative consonants when one might think that there's information in the quote steady state portion of the fricative. The other piece of the speech perception model is that there's extra information at the energy peak of the vowel and at the energy dip of the glide, and this is actually supported by a lot less psychological work. It's really the closest thing to psychology that I can find is an acoustic phonetic study, which did something rather similar to what we're doing. It took a large database of vowels of American English and tried to classify them, and found that in order to classify them, you need measurements covering both the vowel peak and the off glide. They used, I think, measurements at 1/3 and 2/3 of the way through the vowel. The reason that I mention this at all is because our results support this finding. We find that we get better classification for vowels and glides if we look toward the center of the phoneme than if we look at the boundary. The final piece of the perception puzzle is Miller and Nicely's results from 1955, showing that errors in perception of several different distinctive features are independent, despite a wealth of phonetic studies since then showing that the acoustics are not independent.
What do you mean errors are independent? Independent of what?
Independent of one another. So if you turn up the noise and ask people to tell you what consonant is being read off in a VCV or in a CVC utterance, their mistakes in labeling voicing, for example, are independent of their mistakes in labeling place. They factor. The error probabilities factor in that way. All right, and then we have some studies of pronunciation modeling. And the particular model that we're focusing on primarily is articulatory phonology, but the 2 bullet points here that I have here actually apply to most phonological models. Those are that in a VCV utterance in spontaneous speech, the manner of the consonant changes actually more often than not in switchboard data, but the place of articulation almost never changes. And if you have a VCCV, for example, rarely do the features of either of those consonants become something which was not there to begin with. So it's quite common for one of the consonants to adopt place of articulation or manner of articulation from its neighbor, but it's rare for a completely new feature to set in. All right. This leads to the following technological goals. In the acoustic model, we believe from these psychological results that there's some information about place of articulation in a whole series of spectra following the release, not just in any single spectrum, and presumably not just in a delta or an acceleration. But the problem with trying to learn something useful from a dynamic spectrum, from basically a spectrogram segment, is that it's a huge observation vector. Depending on how you code the spectrum, it's between 200 and 10,000 dimensions. So in order to generalize from a high-dimensional observation vector, we've chosen to use support vector machines as our classification algorithm. They do a regularized learning method that essentially tries to minimize an upper bound on the test corpus error rather than minimizing the training corpus error. And our result so far is that the result of actually many different classifications, phonetic classification studies that we've done over the summer, is that by carefully selecting new observation dimensions, you can continue reducing the classification error as you add new features to the vector up to about Up to about n over 6, where n is the number of training vectors that you have. So up to a number of observations which is on the order of the size of your training corpus size. So this is the generalization properties of the SVM do seem to hold up pretty well in our studies. For the pronunciation model, the problem that we're addressing is that switchboard contains dozens of pronunciations per word. And very, very few of them are canonical. We'll have some good examples of that in other talks later this afternoon. But that if you add all of those pronunciations to a flat dictionary, you wind up with too many confusions between different entries in the dictionary. And so one study has shown that, that after about 1.5 pronunciations per word on average, if you try adding more pronunciations to a flat dictionary, the confusions between words start to override the advantage that you get from having multiple pronunciations. So we have two models that we're using to address the problem of pronunciation variability. One is a generative model, as I say, using a dynamic Bayesian network, and the second is a discriminative model that tries to find the particular features of the pronunciation that best discriminate between different words, different options given in the lattice. And finally, it's perhaps not immediately obvious that lattice rescoring is the best test for this problem. We're using lattice rescoring for the following reasons. First of all, the goal of our precise acoustic and precise pronunciation modeling is to improve our ability to correctly recognize words. So it makes sense that we would want to do some recognition problem. We can't do a first pass system for several reasons with either of our pronunciation models. With our generative model, we could do a first pass system, except that the computational complexity is currently much too high for a full first pass system. With the discriminative pronunciation model actually depends on a finite set of word candidates amongst which one can discriminate. And finally, there is some belief that the kinds of observations that we're looking at may be complementary to the kinds of observations that the first pass system is looking at. So we're looking at things that include the Mel scale spectrum, but also include short time energies, formant frequencies and formant amplitudes, parameters from an auditory model, rate scale, auditory cortical parameters, spectral slope, and spectral compactness in 1 millisecond windows. And we believe that those observations are maybe complementary to anything available to the first pass system. And lattice rescoring, unfortunately, is not perfect. One problem that we've had, one problem that we knew that we would have, and intended to find a way to solve and simply haven't had time to solve, is that the boundary times in the lattice are designed by the first pass system to be optimal for the first pass system, and they don't necessarily include everything that we would say is a landmark belonging to the word in question. We have methods on the queue to try to solve that problem, but just haven't had time to really address it adequately. The correct transcription is not always in the lattice. We're getting, I think, roughly a 24% error rate in the lattice, and we're getting roughly a 14% oracle error rate in the lattice. So our headroom, in a sense, is that extra 10% between the first pass error rate and the oracle error rate. Word errors in the lattice finally, word errors in the lattice may be caused by factors over which our system really can't do anything. Word errors in the lattice may be caused by a large difference in the language model scores between the true pronunciation and the second best pronunciation. It may be that the second best pronunciation is something very formulaic and obvious, and therefore the language model assigns it a higher weight, in which case small differences in pronunciation may not be enough to correct that.
Sorry, that was in the first pass system or in the final, where the large differences in language models would swamp small differences?
We're not doing any language modeling. So the large differences may swamp the original acoustic model, and it may be that we're unable to find a big enough difference between those two candidates that we even with the second pass system, we can't contribute information that will change that. And we've seen a couple of cases of that. All right. The systems that we've developed over the summer include, as I said, sets of binary acoustic phonetic classifiers for detecting and classifying landmarks, a DBN-SVN model of pronunciation variability, a discriminative pronunciation model, and a maximum entropy model for estimating stream weights. The DBN-SVN model looks like this, and let me walk through briefly how this is modeling pronunciation variability. The first two columns here are the last phoneme in the word like. The the last two columns here are the phoneme in the word And in this particular utterance, let me play it for you. This is the utterance, like a ton of them were on like, as I'm sure that...
Huh? Say it again.
This is the utterance, like a ton of them were on like. This particular talker says like every fourth or fifth word. This talker also has a characteristic that he rarely closes his obstruents. Most of his stops and fricatives are implemented as glides. So you can perhaps hear that this Laika is actually pronounced as Laya. All right? And a ton of them were on like, let's see. Yeah, there are other examples in this utterance. You can see sort of 4 sonorant patches for 9 words. So
Do you actually understand it, or is it only even after you told me?
I actually didn't understand it until I read the transcription. No, this is a hard one. And this is from the beginning of the utterance file. I've cut off the end of this utterance file, but this is really what the recognizer has to deal with.
You couldn't play the whole sentence. I mean, I assume that from the whole sentence, one would probably.
Well, you might need more context, and you might need context both for
That's what I
both for
said.
semantics and also so you can adapt to the speaker.
Yeah. Yeah, acoustics, yeah, both. Maybe use.
This were a synthesizer, it would be
For
terrible.
this speaker, it's typical that you can understand the utterances, although the first utterance that I listened to for this speaker, I didn't understand at all, but that's before I had inadequate even 1 gram language model, because I couldn't insert like this where the speaker does. Once we'd adapted our internal language model a little bit, we could understand complete utterances. But there are many words by this speaker that when we played them out to members of our group who didn't know what the transcript was, nobody could understand. Out of 5 to 8 people, even working as a committee, they couldn't figure out what the word was.
Yeah.
So the unit of perception is the conversation, not the word.
Yes, possibly so. This is, as I said, this is from the very beginning of this utterance file too. So I guess the recognizer in dealing with this does have additional context afterward, but not before. Just like to point out that the way our system is modeling the turning of K into a glide here is by saying that the K consists of a fronted tongue and a closed tongue, but that in this particular utterance, the closed tongue has turned into a semi-closed tongue. Therefore, when we map that to manner and place features so that we can do the acoustic matching, we say that this is a glide and it's also a palatal glide. The instantiation of glide and palatal glide are these probabilities implemented by the support vector machine. So G sub gr of x is the discriminant, the one-dimensional scalar real value discriminant computed by the support vector machine. And we have the probability of that given that it's a glide release. We have the probability of some other discriminant given that it's a palatal glide release.
Sorry.
Yes?
So the G's are computed by the support vector machine.
Yes.
And the P estimate, how do you estimate? Is that part of the DVM?
It could be right now. It's implemented as just a histogram.
It's a histogram.
Yeah.
So you may have said this, but it didn't represent. So the observation, are the observations at that frame, or do you sort of integrate those over time for the support vector machine?
The observations cover a span of 3 to 11 frames in different systems. Actually, I think we have one that goes up to 17 consecutive 10 millisecond frames. And the observations are selected from a list of spectral, phonetic, and auditory.
So then you
measures
get
for all
one
of those.
support vector machine judgment at every window.
Yes, you get one judgment at every window, and but that window is based on the center frame at that time plus lots of context.
And if they start flip-flopping or whatever, because it's not going to be consistent from window to window. There's nothing that enforces coherence.
We've actually tried lots of methods for dealing with that. One method is to just run the dynamic Bayesian network and let it work out where things change. But actually, Karen will talk in more detail about some of the other methods that we've tried for addressing. There are a couple of problems. One is that that this support vector machine is actually trained to discriminate between palatal glides and non-palatal glides. So it assumes that it already has a context of glide. And the reason that we do that is because we can get much better discrimination accuracy if we focus the problem in that way. But the complication that that imposes is that then that probability estimate is only valid if the center frame happens to be a glide release. And so we need to impose some kind of dependency structure either prior to the DBN or in the edges in the DBN.
So there's no current temporal dependency for the surface, at least in this picture.
Right.
So it's sort of it's context independent surface points.
Yes.
Why are the SVM outputs probability, that looks to me like data given class, which is what you'd want for an HMM, but not what an SVM ordinarily gives you?
It's a histogram, so you can normalize it either way. We've actually tried a couple of different ways of normalizing it, and I think the current best system actually is a posterior probability, but it's a posterior computed assuming uniform prior, assuming that both of the classes have the same prior probability. And so that turns out to be, under some circumstances, that turns out to be proportional to the likelihood. Okay, the other pronunciation model is a model that takes advantage of the fact that we're doing lattice rescoring rather than generative first pass modeling. This system first pinches the lattice in order to form a confusion network, and then looks at the first two words in each of these confusion sets. So the word like, for example, might have been juxtaposed with the word I. By comparing these two words, ideally from training data, but in our current systems, these features are computed from the lexicon, we can determine which sequence of landmarks or which set of distinctive features associated with a landmark are best for discriminating among the word options. And given that, so basically we're turning the word discrimination problem into a phoneme discrimination problem, or into a landmark discrimination problem. That landmark discrimination problem then is computed by taking into account posterior probabilities computed by the support vector machine. And that information is then fed back into the lattice. And finally, these scores then, we compute a variety of scores actually, and there's no guaranteed correct way to incorporate many scores into a word lattice. We want to keep around the original acoustic model score computed by the HMN. We want to keep around the original language model score, and we want to, in addition, add our original scores. So a method that Kimol and Ketrin have been developing here is based on the following observation, that the log probability here is the sum the way that lattices are usually rescored is by adding up a weighted sum of the various log probabilities in the lattice, but that form is exactly the same form as the probability density of a maximum entropy probability estimate. And so turning lattice rescoring into a max-ent problem boils down, in essence, in theory, to the problem of estimating this normalizing factor for each discrimination. All right. Future plans. These are just a few of the future plans, and you'll be hearing about more of them over the course of the day. But the full DBN SVM system is going to be made practical and then tested. Currently, we've tested 2 of the DBN plus SVM systems, and they generally start at about 2,000 or 8,000 times real time, and then by a series of clever engineering processes, we boil that down to about 100 real time and then test it. The proposed task will still be lattice rescoring, but probably on the Hub 5 data rather than RTO3. The second, there are some ways in which one can view what we're doing as a generalization of, in particular, an HMM neural network hybrid system. And it might be one thing that we haven't even attempted to do this summer would be to map out the space between our models and the standard system. And so we have plans to test a couple of models that are some sort of intermediate between our models and the standard system to see exactly what it is about our model that's different from standard systems. We have, several of us will be working on improving the acoustic classifiers both for their own purposes and for rescoring. The maximum entropy lattice rescoring system, I guess, will be used to incorporate prosodic and syntactic and a variety of other word level site information. And finally, there are still interesting unsolved problems, I think, in the question of how one integrates SVM probabilities into a dynamic Bayesian network, especially when the SVM probabilities are computed conditional on some required context. So we're going to look at some of those things. And finally, future plans for the rest of the afternoon. I'm going to leave the technical details now to my colleagues. Amit will talk first about the landmark system. Karen will talk about the generative pronunciation model, and Katrin about the discriminative pronunciation model. Kemal will talk about the maximum entropy system, and then Steve will give some concluding remarks and talk about possible future directions. Then after the coffee break, hopefully we'll make it this far by the time of the coffee break. After the coffee break, we'll have student proposals for post-workshop research, including a set of discriminative word level acoustic models, a model of pronunciation variability, in particular trying to discriminate between talkers, and a study of the acoustic characteristics of some kinds of phonetic distinctions that are not usually modeled in English language systems, but that can be useful in spontaneous speech for reasons that will be described. Other questions about this talk then? All right, if not, we'll go ahead and Amit will give the next talk.
I'm going to talk about distinctive feature detection and landmark-based rescoring. So I'll focus on distinctive and phonetic features. The classifiers use the acoustic observations. Oh, am I not audible? Okay, I'll focus on distinctive features, acoustic landmarks, and the acoustic observations we use in this landmark-based rescoring project. The agenda is I'll give a slight introduction to phonetic features and acoustic landmarks. I'll talk about the acoustic features that we have used in this project. I'll talk about the probabilistic landmark detection and place and voicing classification, and I'll talk about how these things, how these classifiers are finally used in 3 different ways for lattice rescoring. So phonetic features were proposed by Chomsky and Hale, and they can be used to characterize sounds in all languages. There are 3 kinds of phonetic features. Source features target the kind of excitation of the signal, so the difference between the voiced speech and unvoiced speech. The manner refers to how open or closed is the vocal tract, and place refers to the primary location of the articulator. Phonetic features have acoustic and articulatory correlates. These can be extracted for recognition, and it has also been hypothesized that words are stored in human memory as bundles of distinctive features. So here's just an illustration of how phonetic features are used to distinguish between sounds. So here's the z and the s. So z is plus voiced. It has vibrating vocal folds, while s does not have vibrating vocal folds. Similarly, the feature sonorant has continuous passage from the glottis to the outside air, while the minus sonorant feature has some kind of constriction in the vocal tract. Am I audible? Okay, so the stop place feature determines the place of the articulation. For example, plus labial feature determines that the closure of lips has happened. For example, in the sound p, and for t, the constriction is at between the lips and between the tongue and the alveolar ridge. So acoustic landmarks are certain events in time that we are interested in. These are the events that we should look for to find the place of articulation. So for example, the best place to look for a stop place of articulation is at the release of the burst. For example, in this utterance diminish, the best place to look for a place of articulation of D is at the release of the stop constant here. So we have used a number of acoustic features in this project. The rate scale representation, which is based on models of auditory cortex, the long window multi-frequency capsule coefficients, which are the usual MFCCs, the parameters extracted from speech on the basis of knowledge of acoustic phonetics and speech production. We've used formant and related measurements from Yanli's formant tracker, and we've used very short window MFCCs, as these can be highly useful for discriminating stop place of articulation. So next, the probabilistic landmark detection. So we use various classifiers of manner, sonorant, syllabics, continuant, and silence. These classifiers are applied in each frame of speech, and their outputs are converted to posterior probabilities. These probabilities are combined to get probabilities of broad manner classes like vowel, sonorant, consonant, fricative, stop, release, and silence. And then a probabilistic segmentation algorithm is used to find the manner change landmarks. So here's a hierarchy that's used to find the probabilities of these manner classes. So one support vector machine operates at each node of this hierarchy, and a probability is computed. The probabilities are finally multiplied to get the various probabilities. Here's an output of the landmark detection system. This particular example is taken from SVMs trained on NTimit and tested on switchboard. So this person said, yeah, it's like other weird stuff. So as you can see, the landmarks can be pretty reliably extracted on telephone speech. The only two mistakes here are that two glides are missed. The year and the blur are missed. And I'll talk about how we can correct this.
How bimodal is the distribution of the probabilities? In other words, do you get a lot of stuff that's only zeros and ones, or do you get a lot of stuff in between? A lot of instances of probabilities that are in between as the output of these SVMs?
It depends on the training data. If you use a lot of training data, and since we are using histograms for finding the probabilities, if you have a large amount of training data, usually we hardly go beyond 0.95 and below 0.05. And it also depends on the size of the
The
bins.
question is, like, if there's uncertainty in the SVMs, I mean, is it reflected in the fact that you get lots of 0.5s, which then
Yes. Yeah.
continue up to the deviant, so it allows for there to be regions of uncertainty?
Yes, because since we use histograms, if a lot of training samples of both classes lie in a particular bin, the estimate of posterior in that bin will be very close to 0.5. This table shows how we have improved the place and voicing classification at landmarks since the beginning of the workshop. We have seen major increase in accuracy of nasal labial classifiers and other place classifiers. We have built some new classifiers like the rhotic feature for vowels and and flaps. All these are on switchboard. We initially started testing with NTimit, and we observed there was some drop in switchboard, and we have been able to increase the accuracy on switchboard substantially since then. What's that? Rhotic, I basically used it for R, retroflex. Okay, so there are three ways in this system is used for lattice rescoring. The first way is it's used in unconstrained mode. So unconstrained mode means that we don't have any knowledge of what was spoken or what part of the lattice we are analyzing. So we have no knowledge of the lattice. We run the system on speech without any top-down information. So there are two ways this is done, and this is done, and the output of this is given to the DBM-based pronunciation model. So there are two ways this is done. The probability of manner phonetic features are provided in each frame, and the probabilities of place and voicing features are provided at the landmarks. And the other method is where we run each SVM in all frames of speech, and all of those SVM outputs are converted to probabilities, and these are provided to Karen's DBN model, which she will talk about more. The advantage of doing the second thing is that if there are landmarks that we miss because of the smoothing in the probabilistic segmentation algorithm, the DBN may still be able to recover the errors. The second method of rescoring is directly using the event-based system. Here the idea of representation of words by sequence of bundles of distinctive features is used. So for example, here's the word 0. It can be represented as a matrix. So each phone or phoneme, or each sound I should say, is represented as a set of features. And the goal is to given a word and its feature matrix, the goal is to find the probability of this matrix given the acoustic observations. And once we find these probabilities, these are used as scores in lattice rescoring. And each sound can be associated with one or more landmarks. So the way this is done is to compute the probability of the feature matrix given the acoustic observations, and this is split into the probability of landmarks given the acoustic observations and the probability of all the distinctive features given the acoustic observations and the landmarks. And the paths are constrained using a pronunciation graph. Okay. Third way the system is used is to provide scores for queries of a pair of distinctive features, as Mark talked about. So, given a pair of features help in distinguishing two words that are highly confusable, the system is run to compute only those probabilities. For example, it can be used to find the probability of a vowel and the place feature low. So it can be highly constrained only to compute these two probabilities. So to summarize, landmarks can be extracted reliably from telephone speech using support vector machines and different acoustic observations. Combination of different acoustic observations and focus on training has significantly dropped the classification error on distinctive features. Further improvement is required in place of articulation classification, especially on switchboard. Although we have very high accuracies on n-timid, but there's a lot of scope of improvement in switchboard. And part of the reason is that we don't have a lot of phonetically labeled training data on switchboard. And frame-based and landmark-based probabilities from SVMs can be used in various pronunciation models for lattice rescoring. So this is mostly same as what Mark talked about. So we need to improve the phonetic classifiers. We need to integrate the prosodic and syllable prosodic features and syllable structures, and Steve is going to talk a lot about this. We need to assess the system in noise, and particularly we'll be interested in some noise robust observations like the rate scale representation. And we need to do a lot of comparison of our classifiers with the existing ones on telephone speech. This is something we have not been able to do through the course of the workshop. And we have to modify classifiers somewhat for better integration with DBN and the maximum entropy model. And we have to improve probabilistic modeling for event-based rescoring of lattices.
Did you run any sort of experiment to tell you how well you would do in word recognition had you near perfect phonetic feature classifiers?
Yes, we have, and I'm sorry.
Sorry, if this is stuck in your head, just think another question.
We've run a couple of such experiments, but I guess Karen and Kathleen might be the best to answer that. Possibly after your talks, or?
So we ran some experiments before the workshop using the exe transcriptions of switchboard and just converting this detailed phonetic transcription to a feature-based transcription and identifying isolated words for those transcriptions. It's a little bit hard to say how that carries over to actual speech recognition, but it does do a lot better than, say, a regular phonemic baseline.
Since there is some time and I missed a slide, I don't know how. Here's a constrained alignment from, that's how. Here's a constrained alignment. So here I know the start and end time from the lattice, and I know that the multivert is, I think this is the constrained alignment from the event-based system. So you got the vowel, it has to be accurate, but the alignments are very accurate in this case. And they usually are, but the problem with the system is that it does not assume any, it does not have any model of pronunciation variability when we are using it alone for lattice rescoring. So for example, here, at the end of this multi-word, there's the phone T, and the canonical representation of T says that there has to be a closure and a release of the T. So the system forces a closure and a release of the stop consonant here, which is not very accurate for syllable final stop consonants usually. So this is one of the source of errors that we hope to correct, and there are other sources of error. And another thing I've not talked about is the stream weight we got by rescoring using the event-based system alone. So the stream weights that we initially were getting at the beginning of the workshop was like minus 10 raised to power minus 8, and we have
Minus what?
minus 10 raised to power minus 8. And we have increased it to 10 raised to power minus 5 through some very simple fixes, and there is a lot of scope of improvement. Any other questions?
So I'll be talking about the generative model of pronunciation variability that we've built during the course of the workshop. So I'll talk a little bit about motivation, why we want to use a feature-based pronunciation model as opposed to a phone-based pronunciation model. Then I'll describe sort of a basic feature-based pronunciation model that's sort of independent of whether we're doing landmark-based speech recognition or not, which is implemented using DBNs. And then I'll talk about how we combine that with the SVM outputs to create a combined sort of landmark feature-based system. And then I'll go through a series of experiments that we've done this summer and just talk about some observations and very sort of preliminary anecdotal analysis and what we can conclude from these experiments up till now. Okay, so why do we want to do feature-based pronunciation modeling as opposed to phone-based pronunciation modeling? So a lot of pronunciation phenomena that you see in conversational speech, like switchboard, can often be a lot more parsimoniously described using phonetic features rather than phones. And by parsimoniously, I really mean using fewer parameters. And a lot of these pronunciation changes can specifically be described via asynchrony between features and reduction of features, and I'll talk a little bit more about what that means. So there's a number of possible feature sets that we might use. This is the one that we've been using. It's an articulatory feature set based on Broman and Goldstein's articulatory phonology. And so the features are the degree of lip opening. There's actually a lip location variable in this theory that we haven't been using. The tongue tip location, which is the closest point, the location on the palate to which it's closest, and the opening degree, same for the tongue body, whether the velum is open or closed for nasality, and the glottal state or voicing. So all of the descriptions will be in terms of these features. And here are the examples that Mark promised. So these are a bunch of examples that are not so well described using phones and are a lot more naturally described using features. So for example, the apparent phone insertion when you pronounce warmth as warmth is very naturally described as asynchrony between the lip opening and the nasality. And it actually predicts some possibly different instantiations of that P than you might expect if it was an actual phonetic insertion. I don't know is often pronounced as if it had no N or no T for that matter. And that would normally be described as a phone deletion, but if we notice that the vowels are nasalized, there's most of the feature representation is still there, and it's just that the closure degree has been reduced. A more extreme, so this was one example of asynchrony. This was an example of reduction. A more extreme example of asynchrony is if you're doing one gesture with the lips like you would for a V and one gesture with the tongue like you would for an R. If they're sufficiently asynchronous, it might look like two phones have actually switched place. This is an example from the XE transcriptions of switchboard. And this is something that actually requires quite a complicated phonetic rule, but is just very naturally falls out of allowing for a little bit of asynchrony. And here's a couple of examples that sort of throw a bunch of these effects together. Also from switchboard. So it's actually pretty understandable, but if you go to the spectrogram, there's no closures anywhere, and everything's quite reduced, and things are nasalized. This is the word everybody. And it's sort of the same idea. If you allow for a bunch of asynchrony and reduction, you get exactly this pronunciation. Okay, so the main ideas of the approach that we're using, so it's a generative model. So how are the pronunciations generated? Well, we start with a base form dictionary. So here's the base form pronunciation of everybody. We translate the phones into feature probability, and we assign an index value to every position. And the main reason that I point out the index value is because it's useful for modeling asynchrony. So then there's two main types of pronunciation variation that can happen, starting from this base form dictionary. The first one is asynchrony. So what can happen is all of the features will be going through the same sequence of indices, but possibly at different rates. So for example, the voicing feature might spend 4 frames producing the and 3 frames producing the V, etc. While the velum feature might spend all of its time practically in the state and only a little bit in the last couple of states. And so frames where the index values are different between different features is what we refer to as asynchrony. And the degree of asynchrony is the difference between their index values in a given frame. So for every frame, we assign a cost based on how different the index values are of different features. So this is what we do for 2 features at a time. When we have 3 features, the way that we deal with the asynchrony problem is we sort of divide the set of features into 2 subsets of features and measure the difference between their mean indices and have a cost on the difference between the mean indices. Okay, so that's asynchrony. And the other type of variability is reduction, or substitutions in general. So for the lip open variable, for this word, the underlying or the target value would be that it's wide open at the beginning of the word, then it's critical for the fricative, then it's wide open again. But the surface value might actually be narrow instead of critical, for example. So you might reduce that V. And so we have a set of probabilities describing...
I'm sorry, what's the difference between the second line and third line? It says U lip open and S lip open.
So U is the underlying value or the target value.
Meaning what one ought to do if
Right.
one spoke well.
Exactly.
Yeah.
And S is the surface value,
the
which
failure.
is... Yeah. So at the moment, we describe this using context-independent probabilities, just what's the probability of a given surface feature value given the underlying feature value. But in general, we would like to have context-dependent probabilities that depend on syllable, structure, position in the word, etc. We have incorporated a little bit of context dependency during the workshop, but really very little.
How about dependence on the speaker?
That too. It would be more like the speaker cluster, I guess.
Sure.
Yeah. So, well, what we have done is dependence on the frequency of the word. That's the only thing we've tried so far. Okay, so the actual architecture of the model, it's implemented as a dynamic beta network. Yes?
Does your model somehow capture the observation that as you speak faster, you tend to approach the targets less? Is that something you would have to model explicitly, or would it fall out of the model?
It is something that you would have to like have a variable for speaking rate or something like that. The frequent word thing kind of gets at that because they're usually spoken quickly, but not explicitly.
So the cost of asynchrony is not related to speaking rate?
Yeah. Okay, so it's quite natural to implement this kind of model in a dynamic Bayesian network because basically what we have is a hidden state which is factored, and it's a lot more efficient to represent it using a dynamic Bayesian network. So this is an example dynamic Bayesian network that implements this model using a set of 3 features. So each of these clumps of variables is a frame, and here is a zoom in on one of the frames. So these are the variables that we have to keep track of sort of at every point in time. So we need to know what word we're in, what the index values of the 3 features are. Given the index values of the 3 features and the word, we can predict what the underlying values of the features will be, just given by the base form pronunciation.
Index values means the sequence in which they should be produced. But I suppose you can skip them and all that.
We don't allow skips right now. We sort of assume that each feature will at least make an effort to go through every.
But the length of how is it normalized in time?
Well,
I mean, it can go fast. The sequence has to be that way, but it can go either fast or slow.
Right, so it's just like an HMM, but with the state factored into multiple variables. Okay, so now.
So there's another way of saying that all targets are reached even if momentarily. I mean,
Yes.
even if just for an instant.
Well, the targets are reached underlying, so that the underlying variables.
U reaches the
Yeah,
target,
yeah.
the S does not.
Yeah, that's what I meant.
So then this S given U is represented by basically a confusion matrix. Given some value of U, we have a distribution over the possible values of S, and this is sort of what a typical matrix would look like. We typically enforce some sparsity on it because we want to allow for things like the lips going from more closed to more open, but not vice versa. So actually, it turns out that the model has quite few parameters in the end, once we put in all these constraints. So this bit of structure I'm not actually going to go into very deeply, but it imposes these soft asynchrony constraints. So basically, we have a distribution over all possible differences between the indices. And I think that's all I'm going to say about that. Okay, so that's sort of the basic model, and that doesn't really depend on whether you're doing landmark-based speech recognition or whatever. So now we want to combine it with these SVM probabilities. So there's sort of 2 tasks that are involved in doing that. So first of all, we have different variables in the articulatory model and in the distinctive feature set. So we need to somehow translate between these 2 sets. So the way that we do that is quite simple. We just have a deterministic mapping from our surface feature variables to the new variables representing the distinctive features. So, for example, sonorant would be that the glottis is in the voiced state and that there's no major closure in the 3 opening variables. Okay, and the second task is how do we actually incorporate these SVM probabilities? And we do that using the mechanism of soft evidence in DBNs, which is sort of similar in spirit to hybrid HMM ANNs, in that we have one system that produces likelihoods, and then we pretend like we have that likelihood in our DBN. And the way that we do that is we have these, for every variable for which we have probabilities from the SVMs, we have this dummy variable corresponding to the soft evidence. And this dummy variable is always observed to have value 1, and its distribution is set up so that its value is 1 given its parent with the probability given by the SVM for the parent's value. And the way that works out is that you just wind up multiplying in the probability from the SVM with all the probabilities of the other variables in the model. So one issue with this that both Mark and Amit mentioned is that there's a hierarchy in the distinctive features. And it's not quite right to use to use this probability from the SVMs in every frame. So we might want to say that, so velar, for example, only makes sense if we know that we're in a non-sonorant consonant, because maybe not, but anyway, it could. Velar only makes sense in certain contexts. And so the way that we can encode that is to condition this probability distribution also on some other variable, like for example sonorant. So we would only use this SVM distribution if we are in a non-sonorant region. If we're in a sonorant region, we substitute a uniform probability for it.
Just multiplying them this way would mean that you expect the thing generated by the SVM to really be a probability, meaning to have a relative frequency property in the limit. But if it is optimized for discrimination, is it possible that this
well, it's converted to a probability using a histogram. So we do have a measure of how often.
Okay, this is not.
But yeah, I mean, it's not optimized for this task exactly. So we've tried sort of both versions of this, both taking into account this feature hierarchy and not taking into account, and trying to compare. So this is basically how we combine the SVMs with the DBNs, and here's how the model behaves on one utterance. So Millie Coogan has created this tool that will produce an X-Wave script for a given output from GMTK, which we've been using to implement these DBNs. And so what this shows is, actually let me play this utterance first. Okay, good. So what this is showing is the values of various variables in the DBN across time. And actually this is only a small subset of the variables because there's about 78 such SVM features and on the order of 20 articulatory related variables per frame. Okay, so these first three lines are showing the index values of the lips, the tongue tip, and the velum. So you can see there's some asynchrony going on here, and there's some asynchrony going on here. These next three lines are showing just exactly the same thing, but in terms of what phonemes the features sort of think they're in at that point in time. And then the rest of them are showing the actual values of some of the variables as well as the underlying value of the tongue tip open variable. The reason that I'm showing that is to show that, okay, so what's going on here is that the D was sort of implemented as this little dip in energy, and so was the N. And so basically both of them were realized as alveolar glides. And that actually falls out of the model. So if you look at the underlying value of the tongue tip opening is closed during the D and closed during the N, but the actual value is wide or narrow. Oh, sorry, I'm not looking at the right thing. There we go. It's narrow. So what happened is it's an alveolar glide instead of an alveolar closure. But the, let's see. The nasality feature was maintained during the N, even though the closure wasn't maintained. So most of the features are there, even when the manner is greatly reduced. And another nice thing about this example is that asynchrony was used to take into account the nasalization of this vowel. So, so Tom Wong, another undergrad on our team, designed this nasalization detector that we're using here. And so what's going on here is that this O is a little bit nasalized, which the model interprets as the velum staying in the end state a little bit longer than the other articulators. So basically we use this kind of output to analyze the behavior of our model, debug, things like that. And so far we've seen pretty much very reasonable alignments overall. Okay, so in terms of experiments, there's a number of design decisions and a number of forking points. So one question, as Amit mentioned, is what kind of SVM outputs we should be using in the DBN. So one version that I'm calling EBS DBN is that a landmark segmentation is explicitly generated by EBS. And then the place and voicing classifiers are only applied relative to that landmark segmentation. And then the DBN can either be forced to use that segmentation, which we actually haven't tried, or it can take the values of the place features at that segmentation, but it can be allowed to stray from it, which is actually what we did. The second method is that the SVMs could be applied in all the frames and just use the DBN sort of as an aligner and allow the DBN to decide where the alignment is. This can be done in a single pass or it could be done in 2 passes. I'll explain in a little bit why we did it in 2 passes. And another question that we need to take into account is what do we do with the distinctive feature hierarchy? So it doesn't make sense to use these probabilities in every frame. What do we do about that? And there's 2 things that we've done about it so far. One is to use that switching parent architecture that I showed before. And the second thing is to do this 2-pass rescoring. Another question that comes up is how do we avoid overcounting the evidence? So we have a number of distinctive features that are measuring very similar things. Like we have multiple labial detectors, which operate in different parts of the phone. We need to make sure that we don't count that more than once. In fact, we actually probably do have some overcounting of evidence in the model right now that we're trying to sort of figure out what to do with. And the final question is how do we actually train the probabilities in the DBN? So one option that we've tried is to use feature transcriptions, for example, from the ICSI transcriptions of switchboard. Another option is to actually use the soft evidence from the SVM outputs and train with those. We've tried both of these. We haven't seen huge differences in word error rate, but as you'll see, we haven't seen any huge differences in word error rate, so that's not so surprising. So here's a chronological description of a whole bunch of our experiments, or a subset of our experiments. So what we did is for every edge in a lattice, SVM probabilities were computed over the duration of that edge and used the soft evidence of the DBN. And the DBN then computes a score which is proportional to the probability of the word given that evidence. And then the final score of an edge is a weighted interpolation of the baseline scores and the new SVM DBN score. So here's a bunch of experiments. We've basically been doing a lot of experiments on a 3-speaker subset just so that we can do a bunch of things quickly, and then every once in a while testing on the development set. So the baseline, this is the baseline error in terms of percentage and number of words. And then I'll just sort of describe a few of the variants that we've tried. So the first thing that we tried was to deal with this hierarchy in the distinctive features by actually normalizing the values of the probabilities before they're used in the DBN, and training the DBN on hard evidence of feature values from the ICSI transcriptions. Another thing that we tried, we sort of decided that we didn't like this hierarchical normalization and that we should probably be dealing with the hierarchy inside the DBN, so we stopped normalizing the SVM probabilities, and that did seem to work a little bit better on at least these 3 speakers. And we also incorporated the full feature hierarchy in the DBN in terms of...
I'm wondering, in what way do the ICSI transcription indicate that a VLOM is closed? Is it just that you conclude that if the ICSI transcription says there is this sound, therefore the VLOM must have been closed?
To some extent, yes. It's a little bit more detailed than a phonetic transcription, right? Because it has things like nasalized vowels and fricated stops and approximate stops and things like that. But to some extent, we have to make some assumptions. Like if there's a B, we have to make some assumption about where the tongue was. So it's not perfect.
I see. And so you have a table which says that if, even though we can't pronounce a B sloppily. I mean,
We can't.
No, I don't mean it. No. We can't pronounce a B, so it truly sounds like a B, but we didn't do the stuff that we should have done.
Okay. Yes and no. So the transcribers were instructed if the particular sound was something highly unusual and not canonical, and there was no other symbol for it, to mark it underscore with an exclamation mark, so that you know that would be an unusual pronunciation. But that's as far as we went.
But there is only one way to pronounce a canonical peak. And
That's-
everything has to work. I mean, the tongue has to be here, and the velum has to be there, and...
I'm not sure that every phonetician would agree with that statement.
But I mean, that's the assumption
So
on which
you're
they are
talking about
going, right?
identifiability, you're talking about identifiability, meaning if I see the sound, do I know the internal
Yes,
configuration?
right.
Can you
That's
work
what
back from the acoustics to the articulation?
Yes.
And the answer is only approximately.
But this whole method is based on a belief that, that you can do it.
Well, not exactly, in the sense that the DBN can interpolate. If you don't have evidence for a certain feature, it knows that it has to go from the previous target value to the next target value. So you don't have to see evidence for every feature in the acoustic.
Right, but what you're currently doing is assuming that you do have evidence for every feature.
When we do the training from the ICSI transcriptions. Yes, yeah. That's the only time that we
For
make
the
that.
SVM.
Yes, understood.
Right, when we train from SVM probabilities, we don't assume that. When we do decoding, we don't assume that.
So this ICSI, is the ICSI meeting taken?
It's a portion of switchboard that's been transcribed.
Sorry, what was EBS again?
It's the event-based system that Amit was describing. So it's the system that computes landmark segmentations.
Where you only evaluate at the landmarks rather than
Right.
everywhere. Okay.
So initially, we thought that that would be a good way of just dealing with this problem that the SVMs only make sense in certain contexts. But then we felt that the DBN should be using all of the information that we have. And all of the information that we have is all of the SVMs computed in every frame. So then we transitioned to a model that uses that. And the first version of this model was a one-pass system where it used all of the probabilities from all of the SVMs. And it did have the full feature hierarchy in the sense that if you were in a given hypothesis that wasn't where the current context was not the right context for a certain SVM, you didn't use that SVM. But that was a miserable failure, and we didn't even run it on the free speakers because we couldn't get a single alignment to look right. And the reason for that, we think, is because even though we're only using SVMs in the, at the points in the hypothesis where they're licensed, they're still being used where they're not licensed in the sense that they'll have some value in the wrong context, and if that value is sufficiently extreme, it might override something else. If every fricative looks retroflex, then every fricative might get classified as a sonorant, just because the retroflex detector likes it so much. So we decided to do a two-pass rescoring for that reason. The first pass does a manner-based segmentation in the same way that EBS does, because the manner features don't suffer from this context problem quite as much. And then the second pass uses the manner segmentation from the first pass and scores the remaining features. And that has given us our biggest improvement so far of half a
So
percent.
you're doing the one best manner?
One best manner and a full score.
You didn't try like doing
No.
That would be another potentially a little bit more
Yeah,
variability.
yeah.
We had a variant of that in the EBS DBN combination system where the EBS was generating an NBEST list of transcriptions, and that NBEST list was being used by the DBN mechanism.
It was on the queue. I don't think it ever got done, but it's probably still on the queue. But actually, I think we sort of are liking this approach a little bit better overall. But it would be nice to use NBEST outputs instead of the one best. Right now, it's taking us about one night to do one of these rescoring passes on 3 speakers, so it was kind of a limitation.
So is the total number of errors as substitutions?
Yeah, yeah.
Are they very different?
They are a little bit different. The number of changes are just not so big, so it's hard to say if there's a significant difference. I was suspecting that we were introducing more deletions, but I'm not sure if that holds up.
So you think system just changing almost 9 times?
Yes. Right, so not much in the way of word error rate results so far.
Do you have a sense of, I think you mentioned that there was sort of a 10% gain to to be had in the lattice rescore overall. Do you have a sense of, how much would you have gotten with an oracle here?
No, because we don't have Oracle, unless we go through and sort of label the data by hand. We don't. The only experiments that we have on Oracle inputs is the ICSI transcription Oracle experiments that I mentioned.
Okay.
And so there, we were doing a lot better than
But
some.
Here, you just
But here, we
didn't have
don't have the Oracle
transcription.
data.
Okay.
So. Okay, so finally, just one last thing I wanted to mention. One issue that recognizers often have is the relative weighting of the likelihood versus the state transition probabilities versus the language model. And of course, we ran into this problem as well, except now we don't have continuous densities, we have discrete probabilities. And so actually, we need to weight up the contribution of the soft evidence relative to the other probabilities in the model. Or at least this is what we found based on anecdotal observation of the evidence. So we tried weighting it up in rescoring, yes.
How much data did you train your various, models, top or sub-models on?
Not much, actually, and there's not a lot of parameters in the model. So let's see. So when we trained on between like 1,200 and 3,000 word instances. Because we wanted to train all of the training runs on the same data, and so we wanted to use the ICSI data so that we can compare training runs. So we only use that portion. But in fact, the model actually has very few parameters with all of the constraints that are built in. It only has an order.
But what about the SVM itself?
Oh, the SVM is trained on very different data.
Actually, not that different. The SVMs were also trained primarily on the ICSI transcribed switchboard data and also on antenna. So the best ones were usually about 3,000 training tokens for each class.
So do you have any sense what the learning curves look like for your case?
Yeah, for you mean the learning curve in terms of number of training tokens versus performance? On the ones for which we've traced out, on the ones for which we've traced out such a curve, on several different SVMs, once they have been optimized in terms of exactly which acoustic features you were putting into the vector at each stage, all of them wound up having their optimal performance at about number of observations is equal to 1/6 of the number of training tokens.
One more question on the SVM. So you were doing one versus rest in your in computing these values as it was. Were you doing pairwise classifiers for all the SVM feedback?
All of the SVMs were pairwise.
Okay.
What kind of changes are there? Did you look at the outputs in terms of the words?
Yes, but we're talking about 9 words, and
Yeah,
so
but I mean,
yes. So
no, it's not just
so I
9
can
words, right? 9 words.
The right one.
actually it was really very few changes. We found that at least for the current versions of the model that we've been using, we had to use quite a low stream weight, and there were actually very few changes. So I could probably name them.
You changed the word 9 times and got it right.
Sorry?
You changed the word 9 times and you got it right all 9 times.
Approximately speaking. I mean, I think probably in this system there were something like 20 positive changes and 11 negative changes.
What you're saying is that if the SVM BBN system really, really insisted that it was a different word, you took it, otherwise you ignored it.
Roughly speaking.
Oh, that's what high accuracy SVMs. No, that's a different.
Do you interpolate it with the standard HMM?
Yeah.
You do?
Yeah.
And does it get better?
These are the results with the interpolation. Oh, sorry.
No, but if we did it just with the HMM,
Yeah.
what would be the results then?
You mean the baseline?
Well, I don't know whether it's the baseline or whatever, but the most advanced HMM system gives you certain
This is
error rate. I see. And if you interpolate it, you squeeze it out. Yeah. Well, that reminds me of trigrams and a structured language model. I mean, anytime we struggle with language modeling, it's the same thing. The trigrams do very well, and the rest sort of somewhat improves it.
Trigrams and everything that has been done in language modeling for a million years.
But I mean, this these SVMs were trained on so little data compared with the, with the Gaussian acoustic model. I mean, I wonder if it's just an artifact of you not having enough data.
It's not only enough data, it's actually the fact that you can actually have a true transcribe framework, which is what you were saying. So having lots of more data and having true transcriptions at the level that you're trying to classify.
Well, I think you need to find a way to basically not use hand-labeled targets. I mean, that's just not workable. You have to somehow make this work for automatically derived.
Be a transcription effort.
For automatically derived transcription.
No, you need to find a way where normal human beings, not experts, can transcribe it and we can extract information from them. That's what you need to find.
You need
Because
to instrument
there are a lot of people in China, as I pointed out. And if you can employ them, well, I mean...
With this approach, you might actually hurt yourself if you go after the so-called true transcriptions, right? Because then you're actually widening the mismatch between the
I'm not
choices
speaking
that you
of true transcription, I'm speaking about the transcription out of which you could extract information. All right?
You're given a choice among the things that the recognizer considered plausible, okay? Which is, of course, flawed by all the limitations of our HMM system. So to make this particular approach work, you have to actually work within those constraints and do the best you can within those constraints. And that means you have to train something up that improves the classification based on what the what the choices are that the HMMs give you. So you could do automatic alignments on thousands of hours or hundreds of hours in this case, and train up a system like what you're suggesting, but using automatic alignments.
This is what,
good idea.
This is what Morgan used to do when he would do embedded training. So he would retrain the neural network based on the Turby outputs, and then retrain the HMM using the end, and retrain the...
Can we move this?
Something like that.
Sorry, this is discussion to the end, and give Karen maybe 30 seconds or so to finish, and then move on to the
Okay, this is sort of our excuses slide. So, but seriously, there's actually a lot of really stupid things that we should take care of that we haven't. There are things like inaccurate word boundaries in the lattice that completely kill us. There are very short words that we're not modeling well because we always need to have at least as many frames as there are in our DBN template, and we just get disastrous scores on very short words. There's pauses and laughter and non-words that presumably have been tuned by the baseline system that we haven't really thought about at all. And various issues in the actual articulatory to distinctive feature mapping that we need to take care of. More general issues I've talked about already, so I'm not going to talk about it now. Here's just an example of the word boundary problem. This is the same example that I played before. Oops. I'm not going to play it. So the actual edge in the lattice had the word starting over here. So there was a little bit of silence before that I don't know example. And what happened is the SVMs really like this to be a stop burst. And so it put the I in the silence region, and then the rest was don't know, and the alignment is a complete mess. So this is the type of issue that we see with the mismatch in word boundaries. Okay, so just some sort of anecdotal observations that we've made so far. We've seen that we can produce reasonable analyses of interesting pronunciation phenomena. I haven't talked about this much, but after EM training, there's a question of whether these parameters make any sense anymore, and we've looked at them, and they do seem to make sense in the sense that we see the types of reduction probabilities that we're expecting, and that's probably because the model is sufficiently constrained to force that. And we've gotten a lot of ideas for future work. We want to further analyze the types of errors that we're getting. What is it about, one of those 3 speakers I didn't mention, we get a great improvement on, and the 2 others we don't. So what is it about that speaker that was so great? Some more computational complexity analysis. We'd like to run these experiments a lot faster. More context-dependent modeling. We've included dependencies on the frequent words, so frequent words can be more induced than infrequent words, but we'd like to have a lot more types of context dependency. We want to look at the usefulness of different features in the model. Maybe we don't need all of them. We want to have a better understanding of the mathematical issues of these feature hierarchies and overcounting of evidence that we don't completely understand yet, and to explore this use of soft evidence in DBNs in general. It's quite a general model, and it might be interesting to look at it regardless of whether we're doing landmark-based speech recognition. Okay, thanks. Not yet. I mean, we would have to sort of go through it by hand and chop, and we just haven't done that yet. Okay, so I'll talk about the second major way in which we try to use landmark information to improve word recognition during this workshop. And I'm not sure I can do this slide at 3 o'clock sharp when it's right, but let's see. Okay, so this is basically an idea that approaches the problem from the opposite end. Rather than modeling all possible articulatory configurations that could give rise to a certain feature sequence, we look at the landmark output from top down and decide which ones we need to use to improve word recognition to distinguish between confusable word hypotheses. Oops. Presentation. Okay. So the rationale for this is that we explicitly opted to do a lattice rescoring or n-best rescoring approach during this workshop, rather than developing a completely new approach for first-pass recognition. And we know that the baseline system already gives us pretty reasonable hypotheses. So the recognition output that we got from SRI has an n-best list word error rate of 24.4%, and the Oracle error rate on that is 16.2%. So there's actually quite a bit of room for improvement, even if you just try to fix the errors that the baseline system makes. So in order to come up with a manageable goal for a 6-week project, we decided to look at the errors that the baseline system makes, and to use landmark detection only where it is necessary to fix those errors. So we don't use them at all times, but only when we can actually use them to fix errors that the baseline system makes. So here's an example of what I'm talking about. So this is an utterance from the RTO3 dev set from the Fisher subset. The reference transcription of this utterance is that cannot be that hard to sneak onto an airplane. And the best part of the recognition output of the baseline system was they can be that hard to speak on an airplane. So of course, if we notice that there is a confusion that involves very simple phonetic distinctions, like for instance the manner distinction between a nasal sonorant consonant and a stop consonant, or for instance a place distinction between something that is produced with the blade of the tongue as opposed to the lips, then we can go back to our landmark detectors and see if we can actually find evidence for these distinctions in the signal. So in order to do that, we first identify the word confusions. Then we determine the most important acoustic phonetic features that distinguish the confusable words. Then we use our hopefully high accuracy landmark detectors to determine the probability of those features. And then we go back to the n-best list or word lattice or confusion network and use the scores from the landmark detectors to rescore that. So how do we identify confusable hypotheses? We basically use existing algorithms to do this that have been developed before. For instance, based on the work by Mangu, Brill, and Storky, we use confusion networks. So the edges in the lattice are aligned to such that the words that are confusable at similar time points are aligned with each other. And this is the example that I showed before. So we have here the alignment of the true transcription and the best hypothesis from the baseline system. And these hypotheses are ranked by their posterior probabilities. So in our case, the confusion networks that we generated were generated from n-best lists that don't contain foreground probabilities or pronunciation model scores. So they're not actually the best system that SRI can produce. And they have a slightly higher word error rate compared to the word lattices. And also multi-words, for instance, models for frequently occurring word combinations such as I don't know, were split up prior to generating confusion networks. Okay, so how much can we actually gain from fixing confusions in those confusion networks? So the baseline error rate of the confusion networks was 25.8%. And these are the Oracle error rates that we get when we select the correct word from the confusion set. So if we only look at the top two hypotheses, we get a reduction of almost 2%, so 23.9. And this is what we get once we go down further in the confusion network and we use all available hypotheses.
In other words, you don't allow to make a change which is not...
No, we don't allow to make a change in time segmentation. We only pick from the aligned hypotheses in the confusion network, which is of course a limitation, but we decided to start with something simple. Okay, so we also...
the lattice goes to 16.
The lattice goes to 16, so there is a lot more that you can gain when you work on the lattice directly, that's right. And we also compared how these oracle error rates compare when we include or do not include homophones. So homophone words are, for instance, confusions between by and by, so by as in by and by as in by, because of course we can't fix those simply based on the acoustic model. Or confusions between 2, 2, and 2. So that's nothing that we can do anything about by changing the acoustic model. That's basically a problem for the language model. Okay. So then we know that not all landmarks are equally relevant for distinguishing between competing word hypotheses. So for instance, if we try to distinguish between sneak and speak, the vowel features are completely irrelevant for making this distinction. And one potential danger is that if we use all available landmarks, even the ones that are not relevant for discriminating between different words, and if those landmarks get a weak score, that might actually throw us up, that might give us a worse score for a certain word, although there are scores that go in there that should not have been taken into account. The other side of the medal is, of course, that if we ignore certain types of landmarks because we think they're not relevant, we lose some redundancy, and that might be useful in other cases. But we try to select only those landmarks that are relevant for distinguishing between different words. And to that end, we try to come up with an automatic landmark selection algorithm. So the criteria for that are that it should optimally distinguish between the confusable words. It should be discriminative. It should rank landmarks according to their relevance for distinguishing words, so the output should be interpretable in phonetic terms. And it should be extendable to features beyond landmarks. So in addition to simply including the landmarks that we've used in this workshop, some people have suggested using features such as duration or level of stress accent or things like that. So the model should be capable of handling those features as well. Okay, so words have different lengths, so they're associated with variable length sequences of landmarks. And there are basically two options for coming up with a model that distinguishes between different words associated with different sequences of landmarks. One is to use a discriminative variable length model, and the most popular model at this point seems to be conditional random fields that various other people have used in different contexts. And we briefly looked at that during this workshop, but we mainly decided to focus on the other possibility, which is to convert words to a fixed length representation and to use a standard non-dynamic discriminative classifier, for instance, conditional maximum entropy models, or multi-layer perceptrons, or support vector machines. And there has been some previous related work on distinguishing words in the confusion network by converting them to a fixed length representation and then using discriminative classifiers. For instance, Bill Byrne worked on that, and I think also Mark Gales, where basically HMM scores were converted to Fisher score spaces, and then SVMs were used to distinguish between them. So that is something that we can't really use in this case, because we would like to have an input and also classify parameters that are interpretable in phonetic terms, and that can be related back to our landmark classifiers so that we can figure out which ones to use and which ones not to use. So how do we do that? We basically use what we call a phonetic vector space, and for that we use an idea that's borrowed from information retrieval, essentially. So in information retrieval, you present documents of variable lengths by defining feature space that consists of all the possible words, and by defining words as frequency entries in this feature vector. So in this case, we do something similar. The vector space essentially consists of all possible binary relations between two landmarks. So this can either be a precedence relation or a temporal overlap relation. So this, for instance, says a vowel precedes a sonorant consonant, or a vowel overlaps with the place feature high. And then individual words are defined as frequency entries in this feature vector. So this sort of goes halfway between using a complete dynamic model and using a model that just considers words bag of landmarks, essentially. So it's important to note that not all possible relations are actually used because there are phonotactic constraints. So there are some sequences of manner landmarks, for instance, that never occur. And also all the place features are being detected dependent on what the landmark decision was before. So in practice, the dimensionality of the feature space is not the dimensionality of all possible relations, but it's actually a lot smaller. So in practice, it's between 40 and 60. And the word entries are derived by having phone representations plus pronunciation rules that basically spell out which the possible landmark sequences are for those entries. So here's an example of what this representation actually looks like. So these are various binary relationships between landmarks. This is not complete, this is just an example. These are different confusable words. And if we look at this, we can see that some relationships are not discriminative at all because they're identical for all words. But there are others that are highly identifying for certain words because they only occur once in the entire representation. So those are the ones that we want to pick out. And those are the ones that we want to get the scores for in order to distinguish between our different word hypotheses. Okay, and for that we basically use a conditional maximum entropy classifier where weights are trained for certain feature relations defining a relationship between the input and the output. And in this case, these feature functions are the entries in the feature space or the binary relations that I've just described. And then the maximum entropy classifier comes up with weights for these feature functions. So why is it necessary to use a maximum classifier at all? You might think that's actually overkill because if you look at this representation, for a very small set of confusable words, you can pretty much eyeball it, or you could use set difference or something like that to come up with the relevant features. But if you have a larger set of words, or if you include features that are not necessarily binary, it's actually more reasonable to use a maximum classifier that gives you the weights for the different features. So ideally, this should be trained on real landmark detection output, but we didn't actually have a complete training set in our case. So normally people use on the order of 300 to 400 hours of training data for switchboard. And in our case, we only had a very small subset which consisted of the hand-labeled ICSI data, essentially, and another 12-hour subset. So we couldn't really use our full training data to come up with these kinds of representations. So essentially, the model is only trained on entries from the lexicon, but including pronunciation variants. And here's an example of what the kinds of weights are that are actually assigned by a model for this particular example. So in this case, the highest weights are obtained by the relationship between sonorant consonant and blade. So that is essentially the N here in sneak.
What is the SC?
Sonorant consonant. So it's essentially the nasal here that's being picked out as the most relevant distinguishing feature for this particular combination of words. So a different model is trained for every confusion set that we find, which means that different landmark relations can receive different weights depending on the context. So the weights are different depending on which word hypotheses they compete with. Was there another question? No.
How many confusion sets are there?
The total number, I don't know the exact number off the cuff, but it's on the order of thousands.
So that eventually, you mean you're effectively splitting your training data into on the order of 1,000 different...
I'm just training from the lexicon. So I have one training example for each
you
word.
Can generate,
Yes,
okay.
yeah, because we didn't actually have enough training data to really train models from data. Okay, so then we select the N landmarks with the highest weights. And what we could do is scan the bottom-up landmark detection output that we get from ARMIT. But something that Jim suggested was that it might actually be better to use these things as top-down constraints and to explicitly request scores for them
from the landmark detectors. So that is what we do essentially. Once we've identified a relevant landmark relation, we then go back to the landmark detectors and ask them to produce a score for this. So in this case, we would give it the time interval that's identified by the baseline system, so the word start and end times. And we ask the landmark detectors to find a score for these two features. And then what we get back is actually separate probabilities for these two events. And these are then combined using weights to just essentially yield one score. Okay, so then those scores are normalized, and then the resulting probability distribution is interpolated with the one that we find in the baseline confusion networks, so the ones that come from the baseline system. Another way to use them is as additional features in the maximum entropy score combination model, which Kamal will talk about later on. Again, we only apply this to confusion sets that actually contain phonetically distinguishable hypotheses, so we didn't apply this to homophones. We also didn't apply it in those cases where words competed with deletions, because we can't really assign any meaningful features to deletions. Okay. So there are a bunch of different experiments that we ran on this. We varied the number of landmark scores that we use, so instead of using just the top score, the one with the highest weight, or the ones with two scores with the highest weights, or using all scores, we also looked at using just the top 2 versus the top 3 versus all hypotheses in the confusion network. We distinguished between using the entire word time interval for looking for landmark scores as opposed to narrowing it down to where we expect the landmark to happen, whether it's at the beginning of the word or more towards the end of the word. And we made various changes in the feature space representation of the lexicon and tried various score combination methods for rescoring. We also attempted some initial experiments on learning the lexicon representation from data for the most frequent words that occurred in what little training data we had. But that was fairly inconclusive. The main problem seems to be that just using the bottom-up landmark detection output gives the representations that are much too variable to be able to use in the lexicon. But as I said, this is very inconclusive, and we need to do a lot more experiments on that. So I won't go into the details of all of these experiments. These are basically the results. So the word error rate didn't change, so that's very much in line with all the other results that we got. I've shown you the number of words here instead of, or in addition to the percentages, just to show that things did not remain exactly the same. There were actually quite a few changes. So the correct-incorrect decision for the words changed in about 8% of all cases. And there were quite a few errors that were fixed, but also a lot of new errors that were created. So overall, we corrected slightly more errors than we fixed. So there's at least a positive trend, but it was not nearly large enough to actually make a difference in word error rate. And there's a lot more work that would have to be done on this to actually get a real reduction in terms of the percentages. So then, in what cases does it work, and in what cases does it not work? So when we ask for the right distinguishing landmark, and it gets a high probability from the landmark detectors, it works like a charm. So those are really cases where we can fix errors. It does not work in basically 2 different cases. A, when we have a problem in the lexicon representation, and B, when the landmark detectors are confident but wrong. So problems in the lexicon representation. So one example is the word once versus what. So in this case, this was the correct word, this was the wrong word. And this was picked out as the most relevant distinguishing feature by the maxent model. Now the problem is, so this is silence overlapping with blade, which is basically the T here. But the problem is that once can also be pronounced with a T, with a closure before the S essentially. And that was a variant that was not represented in the lexicon. So in this case, because this got a very high score, what was picked out as the correct word. So we hurt ourselves in that case. A similar case is, for instance, can, where the nasal closure has disappeared and there's only nasality on the vowel left, but we're asking for a sonorant consonant overlapping with nasal. So nasal is still present, but the sonorant consonant is gone and there's only the vowel left. So in that case, we couldn't pick out can't as the correct hypothesis. There are other cases where we're asking for the right feature and the landmark detectors give us a high score for them, but they're simply wrong, there's no such landmark there. And that happens very often at word boundaries. So this is another example where these things basically turn into homophones. So much T is not very different from much T, so what can you do in that case? Also, we were in some cases hurt by the word boundaries that were provided by the baseline system, because sometimes they exclude the relevant landmarks that we would like to see in that time interval. And sometimes they include parts of adjacent words that we would not really like to be there. But because we didn't change the time segmentation at all, these are also errors that we were not able to fix in any way. Okay, so we've seen a positive trend, but again, it's not nearly strong enough to give real reductions in word error rate. This method could be used with classifiers other than manner or place landmark detectors. So if you had very high accuracy phone or triphone classifiers, that is something that could be used as well. This can serve as a diagnostic tool though. So the statistics of the score queries across the entire development set basically tells you which phonetic distinctions are most relevant for correcting word errors for this particular set and the particular system that you have. It also provides information about which detector outputs are likely to help, so you can immediately tell which ones help to correct word errors versus which ones create new errors. So this is used for feedback for improving the development of the landmark detectors in the first place. And another advantage is it's very, very little computational effort. It's very, very fast. So if these methods can be made to work at higher accuracies, then there's almost no computational overhead in integrating it into a system. So that was basically all. Future directions are, of course, to improve the landmark detectors, especially at word boundaries. So you might want to have specialized landmark detectors for word endings, for instance. Another thing that we could do is to select landmarks that are not only discriminative, but that can also be detected very robustly. Then again, learning the lexical representation from data is another point that we've only looked at very, very briefly, but that we're interested in. The lexical representation could also be extended to include more temporal constraints, for instance, relationships between 3 landmarks as opposed to 2, and dealing with the word segmentation and allowing more flexible temporal boundaries is another thing that we intend to look at. So that's basically it. Are there any questions? I think we can want to break.
Yes, 10-minute break.
We have to make sure they have so we would like to see
Okay, so welcome back to the second section of the landmark-based speech recognition. There's going to be a slight change in schedule. The students are going to go first, and Kemal and Steve will talk later.
So I should point out that the next 3 talks then will be in the competition for post-workshop funding. So please, those of you who are responsible for that, pay attention.
Okay, so I'm Vidya Mohan. I'm a second-year grad student at the Johns Hopkins University, and I'm affiliated with CLSP. So the title of my proposal, an automatic identification and classification of words using phonetic and prosodic features, were hugely motivated by the work done this summer. So in a nutshell, what I'm hoping to develop in the next 1 year or so is to find some sort of, for every word, build a word model such and identify which phonetic and prosodic features are key to that model in terms of their discriminative ability, and also weight these features such that during recognition, the feature which matters more, so we can use these weights to decide, make better recognition decisions. So the motivation of it will be clear in the next few slides. So the substitution errors form a significant percentage, roughly 40 to 50% of the present word error rates in speech recognition systems. So one of the reasons could be that the phonemes have not captured some finer grained changes in the acoustic, in the speech waveform. So a proposal would be that why not they use the features of the waveform directly when we have to make a decision of, say, confusions or so. So if we want to use the features directly, what structure of the word do we work with? So one proposal is to work with the syllabic structure and its constituent components, because there is a high degree of correlation between the syllabic constituents of the onset, nucleus, and coda and articulatory features. So, for example, the consonant of a consonant in the onset has some leaves a certain articulatory signature in the speech waveform. So if you can model that, and also even the vowel exhibits certain patterns, that would help identify the syllable, which will in turn help in the identification of the words themselves. So if that's the key, then not only do we use these features, we also use these features in an intelligent manner, because some features are more informative and less susceptible to noise than other features. So we want to find out which of these features will be important. For example, in many syllables, the coda is missing. So an consonant, on the other hand, is more discriminative in helping distinguish one word from the rest. So, but the current day speech recognizers, however, give the same level of importance to both the onset and the coda, as well as to accented and unaccented parts of speech. Now, accented speech also help indicate the vowel identity, in that certain vowels, the mid and the low vowels especially, are likely to be accented as compared to the high vowels. So if so the proposal is that let's use more knowledge into our present day recognition systems, and that will probably lead to better recognition. So the proposal is then to build word models which identify which phonetic and prosodic features are critical in the recognition, and to create some sort of a word template for them. A word template will then contain only features and the weights of those features which are consistent for that word across all its pronunciation variants, or across speakers maybe. So if such a word model is built, then how do we evaluate it? So in this particular task, we'll use a word identification and classification task to evaluate it. In word identification, what we're doing is using the word template that was built, find out in what segment of the acoustic speech waveform was this word uttered. So we are looking for a lexical match between the template and a certain section of the speech waveform. So that is one task, and the other task is classification. Now this is a more useful task where we could probably incorporate it into the present continuous speech recognition system, where I think Catherine has already spoken about it. In confusion pairs, it would help if we have the template to help distinguish between them and find the right word. Now what these features are and how the weights will be assigned to them will be clear in the following slides. However, when I'm talking about features in this particular task, these are basically the features that we've chosen are those that we've already have classifiers for. These classifiers were built, tuned during the summer workshop. A list of them will be, these are the list of them. I think Amit and the rest of them have already covered most of it. So basically we are interested in features which preserve as much information of the speech waveform as possible, and for those we have feature detectors for. So primarily they're the articulatory, acoustic, and prosodic features. So here's a list. So given the above list, we want to know which of these features are most likely to be preserved in all the representations of the word where it was recognized correctly. So how do we find these, how do we find the weights will be discussed in the methodology, but this slide will be used to indicate what I mean by a word template. I also have an example. So if On this slide, we showed the structural components of a word. So a word typically comprises of its syllables, and each syllable is characterized by an onset nucleus and coda. There's a distribution in the place, manner, and other features for each of the subsyllabic components. So if our feature detectors found these features useful or recognize some of these features, we want to know which of them are more discriminative in that which of them help distinguish one word from some of the others. So the red ones here are probably not that discriminative. This is just an example, so there's no theoretical meaning as to why I deleted this, but I just resolved. So these are probably not important in recognizing the word because they're probably variable across its pronunciations and so on. However, these boxes in blue probably will go into the feature template because to some extent they're preserved across the pronunciation variations. And also, not only do we include these features, we also have a weight for them so that some of them would be more important than the others.
You may want to, maybe not everybody could see what was behind the blue boxes. You could probably.
Yeah?
Just read the words.
Just read the
words.
Oh,
it's syllable 1, syllable 2, and syllable N, I'm sorry. And here it says onset, nucleus, and coda.
Actually, if you could do the red boxes, that would be good.
Okay, the red here is the number of syllables, the duration, and spectral shape. One advantage of this multi-level representation is that features can be defined at any level of it. So you can have features at the word level, or at the syllable level, or in this case at the subsyllable level as well. So there's a concrete example on this slide. Suppose we were interested in the word center, which has 2 syllables. And this is sort of the canonical representation, say. And these were the features that that I've just tagged to some of these syllables here. Like the onset of, one of the features would be that the onset of the first syllable is usually a fricative, or it is usually voiced, and the nucleus is low front. So if this is a canonical representation, what we'll do is look at our training data and see which of these features are preserved. So we probably found out that usually the nasalization, the coda is usually not distinct, and we might attach the nasalization to the syllable instead, to the nucleus. Or we would have also found that the T is usually, there is no, in terms of voicing, there is just no general trend in the T. So this would be, these blue features would get into our word template. Okay, so how do we find the weights for these features? That will take us to the methodology. So basically, this is the way we're going to be training and testing. So first thing is to find a list of candidate words to work with. One starting point would be the confusable words from the switchboard corpus. Then roughly there are 3 steps to determining the good word templates. The first is feature generation, word template creation, and evaluation. In the feature generation step, what we're trying to do is to get our training and testing examples. So generate all the features, all the possible features for which we have detectors for. And so we have some phonetic classifiers which were developed and tuned further this summer. And this was a stress accent detector which Amit, Steve and I developed. So this was an SVM detector. It was trained on a certain section of the switchboard corpus which was manually labeled as accented or unaccented. Then, I'll be using this as well. The advantages of using the stress accent detector is twofold. One, they give some clue to the identity of the vowel, and the second is that those syllables which are stressed, you can rely on the accuracy outputs of the other classifiers as well. So the use of it is twofold. So once we have our features, how do we decide which of them are important? Basically, we want to use features which preserve as much information of the word as possible. So a natural choice would be mutual information. So we calculate mutual information according to the formula here based on the joint and the conditional probability of a word with respect to a particular feature. So the importance of a feature will then depend on the value of the mutual information. But of course, it will be adjusted according to the accuracy of the classifier and certain stress accent patterns of the syllable. Some syllables are probably more sensitive to context than others. So you can also use that to tune these values that you get for the weights. So once we've got the weights, now at this point it is apparent that there's a there will be a lot of dependencies between the features. So we need some method to sort of reduce the word templates so that the features that we list there are sort of independent. There are techniques for these, but I'm aware of them, but I've not addressed them right now in here. Another issue could be that the feature space is really big. So a preliminary analysis, maybe a PCA or PCA, would help in the task. So this would appear that we are doing some sort of generative model, in that I basically look at the word and in all of its pronunciation variations in a data. We could also look at it discriminately to decide which of the features were critical in distinguishing that from another word. So given this basic methodology, how do we decide if the template we created is good enough? To evaluate that, we have two tasks. The primary one is the word identification task, so where this template is compared with the acoustic, the speech waveform, and that section of the waveform where this probably could have been uttered is isolated. So the first thing is, at what level do we do the search? So it would make sense to do it at the syllabic classifier, because that's the most basic unit in our model. So to use a syllable classifier and to find the boundaries in a particular, in all the utterances will be one of the steps. And then the template will be matched at these syllabic boundaries. Utterances are chosen from the intimate and switchboard corpus, and the evaluation metric will be based on the precision of record. So that's one task. The other is trying to integrate it into a present large vocabulary speech generation, and that could be done at the word confusion pair level. So given, I think this is a summary slide. These are a list of collaborators who would be interested. So the summary is basically, I'm proposing to build a minimal set representation of a word with respect to its acoustic, articulatory, and prosodic features. And mutual information would provide a guiding light as to which features to choose and how to weigh them in their recognition. Then the phonetic classifiers which were developed during the summer will be used. The evaluation will be done on word identification experiments and large vocabulary speech recognition systems. And hopefully the project will provide some interesting insights as to what the key features of the word are. Thank you.
Go back to the slide that has the mutual information equations. So what is F? So in the lower equation, what is
this
F
one?
without the subscript mean?
Oh, okay. This was supposed to be a variable, just the mutual information of a word with all of its features. F is just a feature.
So I'm not sure what F is in relationship to the F1, F2 thing.
Oh, okay. This is a variable, which is summed over all the features.
Okay, so why is there an inequality?
Oh, there shouldn't be an equality. I just put it there for generalization. There shouldn't be an equality. There will definitely be dependency, but I just put it there for that.
No, I don't know if that's just a question. What confuses me is you have a sum over there.
Yeah.
So what is the sum over?
Oh, the sum is over F. That is over all the features.
Is F and F sub I?
Yes.
Okay.
Yes.
So sum over F sub I?
Yes. All the features in the particulars.
And you're assuming that inequality is true, or you're saying that that's a typo?
Oh, this was a typo, but it will not be equal. Definitely.
Okay, so well, then in relationship to this mutual information stuff, so what do you do when you have features and you're trying to keep the mutual information between, say, an onset and a word which is quite long, and where most of the information determining the word has nothing to do with the onset? It's a very bad thing, especially if you're doing something on the sum on the level.
You mean it doesn't make sense linguistically?
When you look at the individual features and the information between features and the words, there's not really a lot of information in isolation. And so I just, again, really into the sum, so.
Is it when you look at the feature and the particular word, it doesn't make sense why it should be there? Is that the question?
Right, it also has to do with the fact that words are variable length. You can have long words, short words, medium words.
Yeah.
And oftentimes the features might be the same.
Yes, definitely.
And the information really, it's really weird to try to find mutual information between things which are usually somewhat fixed duration and other things which are variable duration.
So I'm hoping that, okay, the first question as to whether the feature really makes sense with respect to the word, okay, it may not, but I'm using the classifiers so long as they're consistent throughout I'm using the classifiers that we developed, so if it's consistent throughout the entire corpus or so, that's fine. But they may not have, as you said, any linguistic meaning in many cases. But the other question, could you just repeat that last one again?
Well, I mean, the main question was how can you be assured that you're going to get any meaningful values from estimating mutual information when you have these variable duration things?
I'm not sure, but it appears like generally if the word is long, and in many cases it could be heavily reduced, and if it was detected correctly, then there must be something in that word which probably led to its detection. So mutual information, if it's normalized, I'm hoping is sufficient enough to explain that. But
I don't know if that's what you're looking for, because I thought what you wanted to do, at least when I read these slides, is that W is basically the presence or absence of a word W, and F are a number of features. And it doesn't matter that different words might have different numbers of features that you might look for, because you're choosing between all the instances when the word was the correct word in the sausage, for example, and when it was the incorrect word, and it's the same number of features for that word. Is that what you have in mind, or?
No, basically, I wouldn't expect the same number of features to be, okay. I have a feature here, this feature is the broad feature space which I listed in the slide previously as to the acoustic, articulatory and everything. Now in every instance of the word, these features need not be present, yes. But if the feature is critical in its identification, then I'm evaluating as to, if it's critical in its identification, then it's probably going to be there. And the mutual information will give me the weight as to how important that feature is in the identification of the word. So the feature need not be there in all of it. If it's not there in many of it, it's probably not important. So that's the assumption here. Is that right?
I guess the other thing, so if you've got mutual information, how redundant would the accuracy of the classifier and stress active pattern of the syllable once you've already got, suppose you've got perfect mutual information. So why do you need accuracy of the classifier?
The classifiers are pretty good, but what happens is not all classifiers are accurate at the same level, in that some are more, they have various degrees of accuracy. So when making a decision, I want to make sure that that is taken into consideration. So that is the reason I mentioned that the accuracy of the classifier would be taken, because in many cases you could get...
Why, if you've got perfect mutual information, why do you need, in addition, accuracy of the classifier?
I'm not sure that I would get, right? In the sense that it could, I'm not sure, because it heavily depends on the accuracy of the classifiers. So I have to take into account, there are many degrees of freedom here which I have to take into account. That is the reason I put this down. So.
Couple slides earlier, you had, that one. So you somehow promoted nasal to be kind of higher level.
Mm-hmm.
How does that get reflected? What does that really mean for nasal as a feature, and how does that get reflected in the feature vectors that you're computing mutual information over?
Okay, so you're asking as to how this went there.
Yeah, and then,
right?
And then what happens sort of on the next slide, or the slide where you have the mutual information?
Right. If this particular, this is basically some sort of a canonical representation. So whatever features are there are associated with this particular syllable. So this would also be a feature. Nasal to the syllable is also a feature. But whilst I might not find a distinct coda component, but there could still be some amount of nasalization that's detected. So instead of, since I don't have, when I'm looking for matching a template to a waveform, I will not go looking for a coda component. But if nasalization is a key, then I've already attached it to the syllable. So the presence of it still indicates it is still important. So.
Okay, so you're still looking for a nasalization feature?
Whatever feature is important.
Well, in this case,
Yeah.
you're looking for that. So how does that change what you're doing? Keep going. There.
Here?
Yeah.
How does it change?
Are you saying that the
This
fact that N is not needed but nasalization is needed is a result of this analysis?
No.
No, I mean,
Oh, this is obviously used to, okay, the N attached to a coda might not, the information content of N attached to a coda might be less than, say, the information content of N attached to the syllable. So the mutual information of that could be higher. So the feature here is okay, there's probably a confusion on what constitutes a feature. The feature here is any of the acoustic, articulatory, and phonetic feature with respect to that particular structure of the word. So you can have the word, so it's this feature over here is the term which connects which syllable, whether it's the onset of a syllable, and which feature. So it's not the same feature as the general acoustic, articulatory feature. Those are the bag of features that I'll choose from. But I also have which component of the word that I'm talking about, the information about that. So this is that feature.
Mark, how are we doing on time? Maybe we should Andreas ask questions since we have 10 minutes.
So what kind of classifier architecture are you contemplating for this once you have your features?
I haven't really given that much thought, frankly. So I guess I have some ideas, but I don't want to, it's pretty vague right now. So it will probably become clearer over the course of time. So this is just a proposal for the next 1 year. Okay, thank you.
Okay, I'm going to talk about, or what I'd like to study is pronunciation variability. Basically, I mean, we've seen examples already of some really bad pronunciation, and there's some pretty good pronunciation out there also. I've got a couple of examples. Here's one that's not too horrible. Or not? What?
It's unintelligible.
Okay. Well, that's all right. I mean, you've already heard just how bad they can be, and obviously there are some that aren't so bad. So what I'd like to try and do is identify good and bad pronunciations, both at like the utterance or word level and by speaker as well, and see if we can use that to improve recognition. Because, I mean, for example, you could use just different recognizer structure, different pronunciation models and that kind of thing based on whether it was a good or bad pronunciation. What I've done so far is tried to just see that there is some try to see a correlation between pronunciation quality and the recognizer accuracy. We don't have any data that's actually labeled with pronunciation quality, so I've been trying to work with computing that using an edit distance between the given phonetic transcription and a dictionary of canonical pronunciations for the words. And so originally I was just using based on phone substitutions and additions and deletions. And so the example here is variety. It was pronounced like variety, basically. And this came out just as a 3 because it's just straight 2 deletions and the substitution of the D for the T. But that didn't do very well at all. No correlation with the recognizer error. So then what I was trying to do is do something that would take into account the fact that not all phone substitutions are equal, and some are much more, a much bigger change than others. And so we're doing just based on a simple feature structure where we looked at did the manner change, did the voicing change, and did the place of articulation change, and each of those being worth 1. And so the same example under that, the T to D substitution would only be a cost of 1, and then the deletions are still a cost of 3 because it's changing everything basically. And that did better. So I tried this a couple different ways. This is when I was trying to get a score for the whole utterance. And so what I did is I did that for each word, and then I averaged all the words in the utterance to come up with a score for the utterance. And we got some correlation here. The x-axis down here is the pronunciation score of the utterance, and then the y-axis is the number of errors from the SRI lattice recognizer that we were using as a baseline. And so the actual biggest density is down here in the dark red area, and then it's lighter and lighter. That's just how many utterances came there. And so you can see that basically if it had a really good pronunciation score, it was going to be recognized pretty well. If it didn't have such a good pronunciation score, it might still be recognized really well, or it might not. And I did compute the normalized correlation coefficient, and it was right there, 0.2105, and that was statistically significant. According to MATLAB, the probability of that correlation, if there was really no correlation, was like zeros as far as it went. So there was a statistically significant correlation, just not a very big one. And then I also tried just using the individual, or getting a score just for the individual words, thinking, well, there could be words in the utterance that are pronounced very well and some that aren't. This gave less of a correlation. So what this is showing here is actually the percentage of because it was just when you're looking at only a word, it's either right or wrong in the lattice. And so this is the percentage of words that had that score that were recognized correctly by the lattice recognizer. And so there's pretty much no correlation. I mean, as you get out here, it gets wilder because there's fewer examples. And so the percentages vary more, but that's all that's really going on here. So really, I want to find a better metric of pronunciation quality to be able to do anything good here. And so one of the things that I want to try to do that is fix the word phone alignment, because right now the word transcriptions and the phone transcriptions aren't perfectly lined up time-wise, and so sometimes the phone that's really part of this word is getting scored as part of a different word by what I've got going on right now. And so that could be part of the reason for that it's not getting more correlation than it is. I could also try using a more precise phonetic distance than just 3 features, same or not. And then I'd also like to try using, obviously we need to ultimately be able to do this without having a phonetic transcription for the utterance. And so I would like to look into things like how bushy the lattice is as a metric of pronunciation quality, and also the difference in the score between the best hypothesis and the second best. And another idea that we had was to look at to do the same kind of alignment as I've done up here with or done before with the edit distance, only doing that with the landmark outputs and the best lattice hypothesis. And those would just be different ways of trying to come up with a better pronunciation metric. Then we would need to do possibly machine learning to score new utterances depending on which metric it was. If it's a metric that we can already compute, then we don't need to do that. And then I'd also like to try and do it not just on an utterance level, but for the speaker by speaker, just to try and figure out, is it a good speaker or a bad speaker. And then what we can ultimately do with this is train separate DBN pronunciation models for good and bad utterances or speakers, and hopefully this can give us better accuracy. So yeah, overall we have preliminary experiments that show some correlation between pronunciation quality, but I'd like to do better. Any questions?
I'm a little unclear about how you determine on test speaker, how do you do this alignment? Do you use the recognizer output, the one best from the recognizer, and line it up with the canonical pronunciation?
Well, I mean, we haven't done that yet, and that's one possibility that we're looking at is using the landmark output and then the word lattice. But
Why don't you go back to the slide where you talk?
What?
Why don't you go back to the slide where you talk?
Yeah, I mean, it depends on what the metric is, because right now I've just been doing it with transcribed data, but what I mean.
So you use the forced alignments of the true transcripts? I'm just not clear where you get what are you exactly aligning? How do you obtain the two pronunciations that you're aligning to compute your metric?
What I've done so far is I have just a phonetic transcription that says the exact time of everything, and then I've got a word transcription that says the exact times of each words, except that they don't quite line up, and then I'm just looking up the word in a dictionary. And so for test utterances...
You do this on the phonetically transcribed data?
Yeah, that's what I've been doing so far. And for test utterances, I'd have to do something else, either using the lattice and landmark outputs or some kind of machine learning to identify pronunciation quality. Any other questions? All right.
Okay. I'm Tom Wong. I'm from Georgia Tech, and I'm talking about vowel nasalization detection, which is something that I've been working on during the course of the workshop, and glottalization detection, which is something that I wish to pursue in the coming year. So what vowel nasalization is, the physiological definition, is the coupling of oral and nasal cavities during vowel production. So basically what that means is when you're saying any vowel, there's air coming out of your nose and your mouth at the same time. And so the goal that we were working towards during the workshop was to build a classifier that could detect for any vowel, is it nasalized or not. And so what a nasalized vowel sounds like is, this works?
Yeah.
Okay.
Yeah.
So he's saying you know. And it's what's happened is that in the course of saying the O vowel, he's deleted the nasal that precedes it and just made it a nasalized vowel. And so our goal was to see if we can see where this happens, and if it happens. Now the motivation behind this is that we would like to, well, since the vowel, so in this example in we can, in the phonetic transcriptions, we see that there's no nasal at all. And so if we can detect that there's a nasalized vowel, this could be a sign that there was a deleted phoneme, and therefore we can enhance our pronunciation model. So what we did was we took the switchboard transcriptions and the data and generated training tokens for all nasalized vowels and all vowels. And the training features that we used were mellow frequency Kepler coefficients, knowledge-based acoustic parameters, the formant tracking, and the rate scale parameters. And so the features were taken for each 5 millisecond frame. And the goal was to classify on a per frame basis. So given a frame, is this a nasalized vowel now? And our initial results using a linear support vector machines is a 62.95% accuracy. And so we tried to do better. And what we did was say, okay, if we can divide the problem into a lot of smaller problems, so for instance, for a vowel-specific classifier, so for instance like A versus the nasalized form. And then another thing we did was to try to test our big classifier, which is the one that I just mentioned, on these vowel-specific pairs and see how it does. And also in support vector machine training, there's this notion of picking the best parameter. And we experimented a little bit with a paper by Hasty et al. That talks about the entire regularization path, which essentially computes all the possible SVMs given a range of cost parameters. And it does this in the amount of time it takes to train about 1 SVM, so we can get these pretty quickly. And this is basically a cross-validation experiment. And due to some memory constraints, we did it kind of the old-fashioned way, which is picking a range of values of this cost parameter and training over those SVMs. So the summary of results, what we have, so these are for the vowel-specific classifiers. And so the first one is the linear support vector machine with the default value of the cost parameter. Also, and this is compared to the optimal cross-validated support vector machine, and as well as the first classifier I mentioned, which was the common one. So the outputs of these were combined with the SVMs of other phonetic features and fed into the pronunciation model, which is, as Karen discussed earlier. So one thing that we kind of noticed, which is separate from vowel nasalization, is that sometimes an optimized C value in cross-validation could cause some overfitting. So basically what that means is that I think for this case, in terms of the optimized value was actually performing worse than the default. And this is something that's been examined in question over about in some earlier work as well. So this is the summary of vowel nasalization detection, and these classifiers were put into the pronunciation model. And now I'm going to move on to glottalization detection, which is something that I wish to explore further. So glottalization is another kind of quirky acoustic thing that happens in conversational speech. And it's either a glottal stop or any similar deviation from your normal voice. So the best way to illustrate this is with an example. So what's happening here is the speaker is saying absolutely, and absolutely. Okay, and if you notice, he doesn't pronounce the T at all, and instead you hear this absolutely. So there's this is called a glottal stop, and in the phonetic transcription, it's marked as a Q instead of a T. And another sign of glottalization could be a creaky vowel, in which this person is saying shepherd. Sure. Okay. I don't know how that happened, but
well, there's no D.
Yeah, there's no ER either, but which is trying to my point. So what you were supposed to hear is shepherd, basically, and what that's been transcribed as is a creaky vowel, which is another sign of this glottalization. And in the transcription, indeed, there's no D at all. It's just been replaced by this creaky vowel. And so
maybe it's in the ears.
yeah, this is the extracted creaky vowel. So hopefully it will play. This is what you're supposed to hear after shepherd or shep. That's it. So you don't hear a D, right? So this is a problem. And so this is very different from a canonical pronunciation of this ER vowel, which is in this speaker, he's saying another. 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 Okay, and the extracted vowel sounds like this. So this is different from this. I don't know if you can.
Oh yes.
If you can extrapolate. So the motivation behind this is pretty much the same as the vowel nasalization. Is that if we can detect these quirky things, we can enhance our pronunciation model somehow. And so in this case, we would like to see if there was a deleted T or a deleted D, and if it was deleted, and if so, which one was deleted. So the approach we like to take is also similar to the previous experiment, is we like to extract these glottal stop tokens and these creaky vowel tokens from the switchboard data. And we would like to generate acoustic features for them. And the tokens we would like to generate, one thing that we kind of discussed earlier was that we don't want to extract tokens that are like word initial glottal stops or creaky vowels. We only want to generate tokens that are exclusively ones that serve as an allophone for like a T or a D. And the next step was to train a support vector machine to detect these glottal stops and creaky vowels. And then if our support vector machines are saying, okay, we can't really see these things, then we maybe want to adjust our acoustic features and see if something else can better represent, or something else can better tell, if there is one or not. And then we'd like to look at our current phoneme detectors and see if the mistakes that they're making are because of a glottalization. If so, if we can add our detectors and see how they do. So the acoustic features that we like to use, there's been plenty of work that's been done on this previously. Aperiodicity is one that's been shown to be highly correlated with glottalization. And Heyman and Aka et al. Have discovered that the cepstral peak prominence is a pretty good indication of aperiodicity. In terms of creaky vowels, there's this notion of a wide pitch period or like a low fundamental frequency, and also pitch period damping. And so this pitch period we can probably estimate with an autocorrelation function or a cepstral pitch determination. And finally, the last thing is that there's also been speculation in terms of the relative amplitudes between the first formant and the first harmonic, or the first formant and the second harmonic, and et cetera. And we can get these by viewing like a spectral slice and extracting like the peak or something. And so this is basically a signal processing task that we can do in MATLAB, and we can take these and feed them into our classifier. So in training, we would like to extract tokens for glottal stops, and we like to say, okay, given an utterance, can we detect that there was a glottal stop in that utterance? Also for creaky vowels, if we can determine there is one in that utterance, or notion of detecting a vowel that's creaky versus a canonical vowel, and in which case, if we can detect that, we can also see if there's a glottal stop. And so parameter selection, we could do something else. We could do something like we mentioned earlier, which was using the regularization path, or picking a range of values for our cost parameter. And then if this doesn't work, we can perhaps add additional acoustic features to see if there's some more knowledge we can put into the training. And then finally, we'd like to test and see what happens. So in summary, glottalization may be a sign of a deleted sound. It's often used as an allophone for like a T or a D. So if we can detect these, then we can maybe improve our pronunciation model. And the experiments would be fairly similar to the vowel nasal detection, so the implementation would be straightforward. And those steps would just be detecting these acoustic features automatically, training and testing our SVMs, and then evaluating what happens when we add these to our pronunciation model. Thank you. Any questions?
So what sort of acoustic windows were you using as the input to the SVMs?
I'm sorry?
How big acoustic windows were you using as the input to the SVMs?
This is in
nasalization.
nasalization, they were...
You said they used MSCs for some other things.
Yeah, I believe it was a 10 millisecond window.
So only 10 milliseconds?
And there was short-term MSCs and long-term ones, so it's 10 milliseconds and I think 25 millisecond windows.
Well, the rate scale are very long.
You didn't add additional features? I mean, just in general?
Yeah, we actually tried that. There's been some work that's in acoustic phonology that suggests that in nasalized vowels there's a widening of the first formant, and there's also the lowering of the amplitude. And another thing that we found was that there was sometimes some spectral smearing that we could see in the spectrogram. And so we added those to the classifier, and they actually didn't improve it by much. So we were thinking maybe some of those features were already existent in the features that we had originally.
How much training data did you have for this SVM?
So this depends on which one you're referring to. For the common one, I believe it was 48,000 tokens, around that much. And the way those were generated is taking 5 millisecond frames. And for the vowel-specific ones, we had obviously less because there's less occurrences of the specific ones. I think it was for like an example. I think for AH, I think it was around like 5,000 or so. Thank you.
Well, I'm going to talk about sort of what we looked into in terms of combining scores from different information sources and for rescoring lattices. So as a summary overview, so the goal was to do the lattice rescoring in a sort of maybe a more principled way, discriminative way. And our approach was actually to use a conditional probability model of the hypothesized word on a sausage edge actually being the true transcription. So the fundamental pieces of that actually, I mean, we did use an exponential model and we used the maximum entropy estimation for that model. Bottom line is, we do, the win is really not significant yet. I mean, there's a win, but it's really sort of on the second decimal level. But it seems to be a good framework for including, a new source of information, and I'll go over it now. I'll sort of, in terms of the talk plan, I'll just give a rationale, but I'm not going to spend too much time because I guess Catherine already introduced lattices and confusion networks. And I'll give actually a brief synopsis of prior work. Obviously, there's a lot of work on discriminative score combination, but there are especially two recent papers which are sort of like a minimal pair to this work in terms of they do similar things but in different levels. And I'll introduce the exact approach, talk about the experiments, and show some preliminary results. So this is a kind of a rationale for what we're doing, which is rescoring lattices after they've been transformed into confusion networks. So confusion networks actually allow an upper bound on the word error rate to be directly minimized rather than the sentence error rate, and you would like the information sources to be combined in a discriminative manner. So all these things, to address all these needs, actually we are developing a framework for rescoring of confusion networks based on a model that's estimated in a discriminative manner. So this is sort of what a sausage looks like, and this is from an actual sausage. and these are actually, so again, just to recap, each node is actually essentially an equivalence class from the original lattice, which comes with a time ordering. And once you have such a thing, then you can actually just by using the posteriors, you can come up with hypotheses that minimize at least an upper bound on the word error rate in a direct manner.
What do you mean by that last?
The last plot?
Yeah, the last point. Could you explain?
Sure. I mean, I think when you write this down, it's sort of this is an it's not the way the way the sausages are generated. It's not exactly the word error rate, but actually, I don't know if I could carry out the. I guess
basically
the writer is here.
If you pick the best word at each position, that gives you an error rate, but you could go even lower potentially by realigning those words with the reference. Right? You align the reference to this, and then you can see which one you have to pick at each position to get the minimum word error rate. But you could go even lower if you allowed the horizontal alignment to change.
So a bad alignment still gives you a bound, but a good alignment is a better bound, right?
So that you're referring to the decoder there. So that last point says if you pick a hypothesis from one of those things and you do five such or however many choices there, you're going to maybe not quite do as well as you could. I don't know if you're talking about decoding or estimation.
Decoding, I'm called.
It's not time estimation, it's decoding. It's just like that the lattice can have a lower oracle and then the corresponding pinched lattice.
Of course, yeah.
Lattice you boost the error rate, so it's not the time error rate.
Right.
On the oracle error rate. It's not.
This is another table we have seen before, so there is some room left in terms of these confusion networks that we generate from the n-best lists. And now I'm going to sort of just show two pieces of work which does what we're trying to do. This is a later paper, which does what we're trying to do, but it does it at this sort of sentence error rate level using n-best list. And this is a piece of work which actually works at the sausage level, but uses a different kind of tool for sort of minimizing the word error rate. And this is a sort of a more comprehensive earlier work. So in this later work, essentially in the conditional exponential model, the observed are the whole hypotheses, in an n-best list, and they conditioned on the observations. So then your features are like your scores, and it's something like a word insertion penalty. So when you write this, essentially the maximum entropy model just comes out to look very much like what you do for weight optimization plus the normalization term. And you usually do it over this. You would compute over some lattice or some n-best list, and so this is discriminative, but this is at essentially at the whole hypothesis at the sentence level. And Mangu and Padmanabhan they directly sort of address confusion networks by using transformation-based learning to actually start from a space of parameterized rules and to come up with some top rules. This is one of the I think this was the top rule they came up with. So it essentially boils down to generating a set of rules for rescoring and sort of error correction of confusion networks. By using the rules, you decide whether you need to switch decisions or not. And they did get, on the 97 data, they did get significant. Now, in our framework, essentially what we're doing is we're doing this over sausages. So then now actually the label is just for the word to be correct or not given the context. And the context we take as a general sausage context. So the features that you compute from the context, can take many forms. They can first of all be just a posterior, but they can also be all the other scores that you've computed along the way. And these are the additional scores we would like to include. For example, like a DBN score, any pronunciation model score, and other things. And then weights estimated by the maximum entropy technique. So these are some of the features we have played with. Essentially, along a alignment, you can look at the rank of the posterior as it normalized, and also number of edges in a confusion network. The posterior itself can be a feature, and the model scores could be features. Duration, the number of phones. Also, one of the features could be the relative position in the whole sausage. I mean, how close are you to the start or how close are you to the end? And the confusability. I mean, some words obviously appear on these confusion networks a lot, and you would like to know which ones they are and generate scores for those. And in this case, it's essentially just taking a development set and looking at the most common words that appear and coming up with a score for how often they appear. They can also be binary features along with other, continuous valued features, like if they're members of a set, such as a function word set. And one further caveat is this delete feature. So, a delete essentially, this occurs a lot. This sort of, you either substitute delete for a word, which is an insertion essentially. So delete allows us to see all of the errors introduced as substitutions. So for the delete, essentially, if you introduce a feature, a binary feature, which is only one for deletes, so this is a way to sort of divide the space into two, such that for a specific feature, it is, all the other sort of feature values you can essentially, one way we've tried is just for all the values that do not exist, you just set to 0, but it's just the delete feature is a binary as 1. So in this way, any kind of sausage you can make use of during your training, because everything has been sort of recast as substitutions. So within this framework, I tried with several things. I played with several things, and the whole framework actually came together, like the sausages and these kinds of things came together kind of relatively late, and so probably I really couldn't do as much experimentation as I wanted. But one of the things is obviously looking at different sets of features. Also, the other thing that proved useful was using, so to apply this in a safe way, in a way. And one thing you can do is to come up with a simple confidence score by looking at the ratio of the posteriors of the top two scoring hypotheses, such that if, if the system is really, if the sausages are really confident that the top scoring word is sort of safely away from the contenders, essentially not touch that. So that gives you another another parameter. Now again, like I mentioned, so there's this major decision about how do you actually deal with the delete edges. So you could essentially just leave them all out, or by include them with the delete edge, and also the other thing is during training, while you're picking your training samples from a reference aligned sausage, how do you how many of these essentially do you pick up? You can pick up the one that actually matches the reference, but plus you could go as deep as you want. In terms of false examples. So in terms of preliminary results, I have worked with the so sausages, again, the RTOT development set sausages, which come in 2,930 files. And for this kind of work, I mean, I divided into a training and a testing set, which consists of 2,930 files. And so there is some, there is some gain. It's just not reflected in the word error rate. So it's on the order of, tens of examples fixed, while things cancel each other. And there are some improvements. Well. So this is actually, so confidence kind of works. Okay, so, well, this is actually, I should say, this is a completely this gives no information here, they're all the same. There are differences. The thing is, there are again, maybe tens of examples where we deviate from the baseline, but we really, this isn't, first of all, there are several problems with this because the first one is this ran like last night, so that's a big problem. But the other problem is the sausage error rate is here actually high. With respect to that, and it should actually be lower because these come directly from dataset. So this is something I need to sort out. So I don't know how I managed to do that, but this is one example where we tried to use the DBN features, but it's it is a promising start.
Why?
It just feels that way. No, the thing is, first of all, the first two, we should separate. These results have nothing to do with landmarks, first of all. This is a general technique for combining stuff, and this should have worked. It should be actually.
Why shouldn't it work?
Sorry?
Why shouldn't it work? People have agonized over how to rescore latitude.
No, when I say worked, like worked at the 0.3, 0.4 level.
But who has results showing that it has in the past? Like Dimitra agonized over getting these things to work and was never able to.
Right. Well, I guess I went through more of the same agony, I guess.
No. She went through.
You're here for the summer, she was here for 6 years.
Yes, 6 weeks.
1 year, 6 weeks.
And I agonized.
Well, yet another data point, but like I said, this is and so this doesn't really, speak about. This only speaks about my implement, or how whether something can be gotten this way from sausages at all, rather than the landmarks themselves.
In our experience, you have to build the sausages differently.
Well, actually, in this workshop, we have not looked into different ways of building sausages. So we just started from. But the thing is, it's I don't know. It seems like you see all these anecdotal examples which suggest these features, and somehow just doesn't go down. I would still like to have a little bit more of this. So I would like to see how, probably, can these things be informed by completely outside sources, like things you get from prosody, either stress accent levels, duration, or because we have at SRI we have built a large database of very interesting prosodic features, and since this is a framework which is ready to swallow in a lot of features and see what it can do with them. So I would like to try some of that, and there are obviously other things. Like one other thing is, I guess you already, you may remember from Millie's talk. I mean, other features you can include are actually like some speaker characteristics or what the utterance looks like. But I guess, people should still keep suffering in this framework. That's what I'm arguing. And I guess that's my talk.
It's just for tomorrow. Okay, Steve, if you want to close this.
So you'll be relieved to know that there are no more word error rates. And so this is more of a post-mortem in that I'm not going to talk about what I did this summer because I didn't think that would be very interesting given everyone else did much more than I did. So I thought it would be actually more interesting to talk a little bit about what we've learned from this summer and how we might use that knowledge for future generation speech recognition system design, using some words of insight. So, again, this is my opinion, not that of anyone else in the group. So what is wrong with the landmark approach as it's currently instantiated in the systems that you've heard described? Well, among the most important, I think, that are not necessarily correct in terms of the assumptions, is that the speech signal can actually adequately be characterized by merely a sequence of acoustic signatures, which we call landmarks. This is, I think, an act of faith, and I'm not sure it's actually one that is substantiated. Secondly, the acoustic signal can be mapped back to articulatory configurations that can be modeled with some degree of precision. This is really the basis of Karen's DBN model. And again, I'm not sure that this is really strictly true. It may be partially true, but the devil's in the details. Lexical models bear some systematic relation to sequences of acoustic landmarks. Again, I think is an assumption that is not necessarily borne out by switchboard. And finally, that such landmark-based clusters are actually sufficiently discriminative at the lexical level to significantly improve recognition performance relative to conventional phone-based systems. And I think this gets to Fred's point, which I think is a very important one. And so in my view, speech is actually not a sequence of landmarks at all. That the landmark approach, I believe, is essentially a passive acoustic detector with a variable and potentially uncertain, and that's crucial, potentially uncertain relationship to speech production. The acoustic properties of the speech signal, therefore, may be viewed as an inevitable consequence of the articulatory movements associated with the words, or maybe not. Within this perspective, words are, at least in my view, still viewed essentially as sequences of segments, with the caveat that there is some articulatory properties that may be synchronized, but in some sense, this is still, in my view, a segmental model in sort of DBN and acoustic landmark clothing. And so what's missing from the current approach, in my view, is what you could call negative entropy of information. And I'll get into a little bit more as exactly what I mean by this. But with respect to the task at hand, I think that this concept of this entropic dimension translates into acoustic patterns that are really able to distinguish among words. And sometimes it may be at the phone level, sometimes at the syllable level, and as one example played to you earlier today, sometimes only at the conversation level. So you actually have different time frames, and you can't a priori predict which one is actually going to be discriminated. I think this is a real problem. Okay, so one approach to applying this principle is through the confusion networks And Katrin has described some of that, and Kamal has described some other approaches. I think the problem, from my view, of confusion networks is, as Katrin mentioned, as you really are relying on huge amounts of training material, and that this really limits the approach. And I think that it was remarkable what you did, given the limited amount of training data. I think what you really want to do in the long term is to minimize your reliance on training data, because, I mean, let's face it, it's hugely expensive to annotate, to collect, to order, and the extent to which you can minimize your reliance on training data, you're far better off if you can figure out how to do it, which is the $64 billion question. So what is required to develop a non-phonemic approach? And so that's what I want to discuss in the next few minutes. And these are just ideas, some of which were sparked by the work done this summer. So I actually feel that this is actually an extremely valuable summer. I think for all of us in the group, because I think that the future of speech recognition may actually have been partially born in the work that we all did, even though it may not quite seem that way from some of the results that were shown. Because I think that we learned a lot. Okay, so in my view, currently the ASR systems don't attempt to explicitly segment the speech signal. I think this is a big mistake. There's no attempt to estimate the number of words, the syllables, or other constituents before recognition. In other words, the recognition comes first and then you try to figure out what the segmentation is. I think this is a big mistake. Nor is there any considered effort to delineate the linguistic structure prior to that stage of recognition in terms of what the stress pattern is like, how many words, whether those words are foreign or not, et cetera, et cetera. If it were possible to accurately estimate the number of syllables, et cetera, and their temporal demarcation and many other aspects of the speech signal, I think that the act of recognition would be much simpler. And I think this is actually what humans do most of the time. So for one thing, it would be possible to estimate the number of phonetic constituents, say, within each syllable, and also to ascertain whether the syllables are likely to be independent constituents or whether they're bound together into the same word or word compound. And segmentation, I think, can actually be performed with a variety of methods, as I'll just quickly delineate here. With neural networks, this is work that Lakendra Shastri Chonchang and I did a few years back, and we got pretty good results. Other people like Hanamurti and her colleagues in Chennai have done similarly successful experiments. You can do something that would look like this, where the yellow sort of reveals the energy contour. This is from Pratt, and which gives you some rough idea about the syllable segmentation. Because there are so many constraints on syllable structure, if you're able to delineate this, you actually have solved, I think, a lot of your problem. Also, you can use manner of articulation classifiers to delineate segmental boundaries, which most people call phones. And you can do that by looking at the confidence levels and seeing that there's a relationship between that and the classification accuracy, and then actually exploit the lack of accuracy and lack of confidence on the edges to actually do implicit segmentation, which is what I have done with colleagues at ICSI. And this is just output from the ICSI transcriptions of Switchboard, where we have done manner of articulation classification that is pretty concordant with that of the phones. You can also use this type of approach to pick out the centers, the nuclei of the syllables, because we have very good vowel spotters that are accurate to about 95 to 98% accuracy. So at the very minimum, you can actually pick out the centers of your syllables and then try to delineate what's in between. And I was talking to Oded Gitsa earlier this week, and he said that this is what they had actually done at Bell Labs just before he and Mohan Sandhi had left. They focused on the vocalic nuclei. Okay, so in terms of the phonetic classification, well, you've heard about all of these different articulatory acoustic features today, and I won't belabor the point, but essentially what you can then do is to delineate these features given the segmentation that you've done at the syllabic and at the phonetic segment level. And finally, the stress accent, which is the syllable emphasis, is extremely important because there's a tremendous amount of variability in the phonetics in terms of which phonetic segments occur, their durations, their energy levels, whether things are deleted or not. And there's a wealth of data, and so we know that this is important. It's the single most important factor, in my view, in predicting the pronunciation variation in the switchboard corpus. And so you can utilize this information. So a few years ago, Sean Chong and I developed one for switchboard, and this summer, Vidya Mohan and Amit Juneja developed one here as well using SVMs. It works pretty well. And so you can use these features of duration, normalized energy, and vocalic identity to define that pure and simple. And so as I mentioned, stress accent affects many phonetic properties here. And to my mind, the reason why it has such a tremendous impact on these phonetic details is that these phonetic details are reflecting the information content. And not just in terms of word intelligibility, but in terms of emotional nuance, subtleties, back channel sort of information. And that stress accent is, in my view, the single most sensitive acoustic property of the speech signal that reflects the information contained in the speech signal. And that this is what determines, in my view, the pronunciation variability, not the sloppiness of the speaker. Speakers are not sloppy, ever. This is a Freudian view that there are no accidents. People speak exactly the way they do for very good reason because they're trying to communicate something special that can't be encapsulated just by the words themselves. And so they do it through how they pronounce the words. So syllables that are lexically and semantically discriminative are far more likely to be heavily accented, heavily stressed than their unaccented counterparts. That can't be for a coincidence. It's got to be because the speaker essentially has a model of the listener's view of how to decode and speaks to ensure, to maximize the probability that the listener is decoding properly. And you use things like nodding of the head, aha, and things like that as feedback. And so you have a very intricate duet between the speaker and the listener. And so the speaker, when they put emphasis on a certain syllable, it's because they feel this particular syllable, this particular word is particularly important for decoding on the listener's part.
Aren't you assuming that what the speaker wants to communicate is sense, rather than, for instance, that he's macho?
Well, you can never be sure what a person is trying to do. The reason why in switchboard I'm fairly confident that it's truly communication of information is because in switchboard you have sustained conversations of 5 or 10 minutes length. And if the information wasn't effectively communicated, there would have been a breakdown.